Preparing to live stream on the meeting. Bun, să caut și pe contul echipei contul. 24 hours. Preparing to live stream on the meeting. What?
Hasn't begun?
Da, nu înțeleg de ce a început. Nici măcar nu
Gata. Gata, a
Bagă.
început. Are delay de 10 minute când apare pe YouTube.
Mhm.
Ai ideea. Deci o să ia ceva să apară pe YouTube, ne închidem camerele și așteptăm speaker-ul.
PPT-ul. Nu uitați de PPT.
Stai, am o idee. Îi dau pauză și îi dau eu.
De start care delay. Lasă-l să meargă, că nu contează.
Ok. Bun, am o idee mai bună. Îl las puțin pe privat până intră ăștia și după aia... Așa. Ia stai. Am o idee mai bună. Îl pun pe 19 decembrie la ora 1 să înceapă.
Nu mai vorbim aici. Nu mai vorbim aici.
Hello everyone, my name is Stefan. I'm from FTC team Roto-D2 and I welcome you to the event 24 Hours of STEM. I am really glad you are here with me. I hope you have enjoyed your event so far. And our first speaker will be Naman from FRC team 7539, also called Elevate from Mumbai, India. Welcome, Naman.
Hey Stefan, great to be here. So glad I could be a part of this event.
I heard you'll be presenting on the mechanics of FEA, and I am really glad to see your presentation. So whenever you can take it away.
Yeah, sure. So I think first I'll just sort of start off with explaining what exactly is going on here, because my presentation is a bit on the unconventional side. So basically, the theme of this is sort of the idea of jugaad, which is a very Indian term, and the idea is basically sort of creating things in sort of unintended way, and it's essentially being scrappy. So I felt like that theme sort of fit this quarantine environment perfectly, and I'm basically going to be trying to sort of deliver that sort of like lecture experience with different diagrams, with different models and all. And the great thing about this is, because these were all just sort of made stuff that I had lying around. These are all, things you can actually sort of see the different.
Hold on a second. We can't really hear you right now. I think like your
and you can see,
connection is
all of the
unstable.
crazy things that come out of it. So, okay, let me try moving over to hotspot.
I think it's fixed. You can try talking now.
Yeah,
Okay.
I hope everything's okay on your side.
All right, is it better now?
Your camera is blocked, but we can see the stream from the phone perfectly.
Yep.
Oh, okay, your
Okay.
camera is fixed now. Okay.
All right, perfect. Okay, so I think I'll start off with the basic question of what is FEA. So FEA is, and I hope everyone can sort of see my setup with the camera on whatever I'm writing down here. And let me just write a bit bigger. So it's
Yeah,
you can
that's
see it.
perfect.
It's mostly going to be so it's mostly going to be diagrams and stuff. So it is finite element analysis. Now, those are a lot of big words, but essentially what I'm going to be looking here is talking about how you can take something like a robot and turn that into a bunch of questions on, how do, like, let's say, for instance, if I have a shooting mechanism, how can I look at that and say, all right, will this work? Is this suitable? Turn the question of will this work into given these forces that an FRC or an FTC robot will experience, will the structure fail, or will it be able to withstand that? What kinds of deformations are we looking at? So it's basically sort of turning these very sort of broad, difficult questions into easier questions that can be mathematically analyzed either by hand or through software. So with this, I'll sort of be looking at building both a mathematical and an intuitive understanding. So it really works towards where when you're creating mechanisms towards the beginning, you can sort of understand more or less, what doesn't work. You have that idea in your head, and once you made something, you also know okay, now how can I test this? How can I get this in a simulation? And how can I show that, this will work? So I think I'll start off with this thing. So it's sort of an interesting diagram in terms of forces. And I think if you can look over here, you'll sort of see. So this is called the impossible string. And it's an interesting sort of look into how tension works, where I have this ribbon that is standing perfectly upright. I'm only supporting this from the bottom just so that it doesn't fall. And, just through what is basically just a laminated sheet, it's able to stay up. And in that sense, it's a case of how does this work? So if we look at this, you can look at each individual component as one thing. What's happening is that each sheet wants to expand outwards and become flat. But the toothpicks here are preventing them from becoming flat. And this is sort of chained over on and on. And if you look at a much simpler version of this, you can take it down to just a single example where, let's say I have like a ruler over here and I'm just bending this and I'm just hooking it on. And this looks a lot like a bow. And this is sort of exactly how bow functions. You're putting the string under a lot of tension. And when you pull it and you release, it's sort of all let out. So it's sort of really interesting to look at how with these, with, something as basic as the concept of tension, this is something that, anyone in high school would have learned in physics class. You don't immediately see how that comes to this. And really, when you look at these edge case examples, that's where you can really understand how these work and better understand how you can apply this to basically anything. So I think I'll start off with the very basics of your structural analysis. So I have been here and I'm only going to be looking at normal forces. So there are two kinds of normal forces where you would either have what is a pulling force. So you're just pulling on both sides, which is tension, or you have a pushing force like this, which is compression. And this is essentially how you would draw diagrams. So, a common question is, well, why don't we just draw one arrow to show that it's sort of being squeezed or stretched? But the issue is that you have to look at this like an object in space. If you just push it from one side, it's going to move. You want to push it in such a manner that it stays still. If you were doing a free body diagram, you would sort of show that there's no force on it, but you're looking at what happens internally. So for example, let's say if I take an object, rubber band over here, and I stretch it, I pull on it here, obviously it's going to stretch, the length of this is going to increase. Now, if I do the same thing with a metal rod, you won't really see that happening, but it is happening. And when forces become very large, that's when something like this becomes significant. So the idea is that we can then mathematically express what this is. So one idea that we look at is making the forces non-dimensionalized. So let's say, for instance, how can I have that same understanding if, maybe on a rod, which has a 1 mm diameter versus, let's say much larger rod with, a 1 cm diameter. If my force is the same on these, then obviously I'm going to get very different results, even if they're made out of the same material. But what we want is we want some kind of property where if these are the same material, we get the same result out of them. And that's where non-dimensionalization comes in. So what's really important is the idea of a stress. So you have a stress, which is equal to force upon area. And in a lot of ways, this is very similar to pressure, especially at a very basic level. Although there are some slight, nuances that make stresses different from pressures, such as looking at the loading conditions and all. For a very general understanding, you can think of it as a pressure. So essentially looking at that force upon an area, and that helps you, that again helps you get that intuitive understanding for how things work. everyone knows that if you have a very thick piece of metal, it's going to be a lot stronger than a very thin piece of metal. That's why, let's say, if you have a sheet of aluminum that's 1/16 of an inch thick with your hands, whereas obviously you can't do that with just a slab of aluminum. So that's a really key point here, stress. And stress is sort of what the material experiences. If two pieces of aluminum experience the same stress, regardless of how they're shaped, they are equally likely to break. The breaking point is the same for every element. And that's why it's really important to know what stress is and to minimize your stresses. So from stress, you get the idea of what is strain. And with strain is you're looking at the change, you're looking at a change in length. So for instance, if I have, let's say just a one-dimensional line right here, I'm pulling on it, and then it increases in length by a certain delta L, and this whole length is L. Your strain is equal to delta L over L. And what's really interesting is that you have a direct correlation between stress and strain. So you can actually just say that the stress is proportional to strain. And this is better written as Hooke's law, where like that stress sigma is equal to Young's modulus, which is capital P, and then strain, which is epsilon. Now, so this is your strain, this is your stress, and this is Young's. So your Young's modulus now becomes a very important constant, and it is, your Young's modulus is a material property. Every piece of aluminum will have the same Young's modulus. And that means that now I can look at what the difference between materials is based on the Young's modulus. I can tell how elastic they are. So for instance, if I go back to my rubber band, a rubber band obviously has a very low Young's modulus. I'm barely putting in any force and it's getting a very high strain. So that's why your Young's modulus becomes incredibly low for things like rubbers, but it becomes much, much higher for things like metals. So as an example, aluminum has a Young's modulus of 68 megapascals, and mega is 10 to the power of 6 pascals. So that means that you would really need to put a lot of force just to have the strain, just to sort of get a very visible strain. And that's why generally the strain values that you deal with are very, very low. So, if you look at, let's say, the force put by, like a 2 kg weight, that's 20 newtons. And if that 20 newtons is, let's say, over an area of half a square meter, that's 40 pascals. So it's orders of magnitude lower than the Young's modulus. So that's why you very rarely get that stretching. But that what's really important is the cross-sectional area. That's where if you have very thin components, they can bend very easily. And that's where your Young's modulus becomes incredibly important. Do you want something to be stiff? Do you want something to bend? In cases, it's very important for things to bend. So many mechanisms are really built on the energy that you get when things bend. And it's really important to know how your Young's modulus works, to know how the object deforms, to really work according to that. So this is basically your normal forces, which is compression and tension. And although sometimes things do fail in tension, they very rarely fail in compression. And generally, it's quite rare that you really have failure on either of these loads. What is a lot more common is having failure on load called shearing. So shearing is a bit more of a difficult concept conceptually, but it's also really important. And believe it or not, the math with shearing is actually a bit easier than with normal forces. So shearing requires a bit of a weird how it's defined is when the force is parallel to the plane. So, all right, here we have a force that is parallel to the plane. But wait, then the object moves upwards. All right, so we need a force parallel to the plane here. But this diagram, because now these forces are acting in opposite direction, and they're causing this sort of shape as a whole to rotate. And obviously, we don't want that. We want it to be in translational equilibrium. We don't want it to move. So on top of that, I have to actually add a force here and over here, which this is essentially what your shearing diagram looks like. And it seems very weird that you have these four forces, but they're all sort of kept there for a reason. And just to clarify, all of these forces are equal. So if you're saying that it's being sheared by a force of, let's say, 4 newtons, it means you have these 4 arrows, and all of these arrows are 4 newtons. So that's a really important point to know. And again, you can sort of do the same stuff with shearing. So you can say that with this, now your deformation looks slightly different. We sort of have the body deform like this. And your deformation would basically be measured as this delta L over length. And in this case, the length is this one. So this is your L, delta L. And an easy way to remember this is if you take this angle as theta, your shear strain is equal to delta L over L, which is also tan theta. If you guys remember SOHCAHTOA, it's opposite over adjacent. So it's equal to tan theta. So quite often people would actually sort of measure the shear in terms of the angle, but the official, the sort of more correct way to measure shear is by the tan of the angle. So, obviously then you can have very high shears and very low shears. You're not sort of compressing everything in a range of from 0 to 180 or 90, depending on the diagram. So this is really important. And once again, you know that the shear stress is proportional to the shear strain. And once again, we can write this in terms of Hooke's law, but it ends up being a little bit different. So your shear stress is equal to your shear modulus times your shear strain. Now this looks very similar to what we had with your normal forces. Now one key point is that what is the relation between your shear modulus and your Young's modulus? So there is a slightly complex notation for that, where it is in terms of Poisson's ratio, which is sort of a whole other thing, which we'll not cover this time. But basically, for the most part, as a general rule of thumb, you can take it that the Young's modulus is equal to the shear modulus times 3. So that is a really important result, because that means that your shear forces are more or less 3 times more important than your normal forces, and that's why you have to pay a lot more attention to shears. And I think there is a question in chat. All right. So would the phenomenon of shearing occur if there are unequal forces, or is it solely based on their quality? So yeah, that's a great question, and it really comes down to your force diagrams. So let's say, for instance, as a very simple example, if I would take it as, let's say, 10 newtons here, 10 newtons here, and let's say 5 newtons here, and 5 newtons here, what would happen is that this would then start rotating. I'm assuming this is a 1 by 1 cube. This would start rotating with 5 Newton meters of torque, and then so basically 5 newtons of each of these goes into that rotation, and then now you get a shearing with 5 newtons everywhere. So it's sort of, again, you're sort of adding to the complexity. If you have unequal forces, essentially you sort of see where the forces go, and that can give you where the shear is. So a good way to look at it is basically take the lowest force. That is going to be the shearing force, and the rest sort of all goes into translation. So obviously, in that case, you will have to be very careful about what forces you're labeling, because let's say, for instance, if you're looking at maybe pushing a plane while it's in the air, it's you're not just giving so like let's say if you have a plane like this, um, this is a terrible rendition of a plane, but assume that this is a plane and you're pushing it upwards. That's not the only force there is. You have to account for the fact that there is air resistance below it, and that is sort of why you can let's say damage an object by hitting it, even if it's not supported against anything, because you would have to hit it hard enough that the resistance, whether it's the friction, whether it's the air resistance, whether it's just the inertia of the body itself, is sort of is there to oppose your force, and that's where the stress comes in. So obviously, if you're looking at something like inertia, that becomes more complex calculation that goes into high level math. But it can sort of all be condensed down to this conceptually. If you have to do the math yourself, that's a whole other topic. But that's why we have software, so you can understand the math first, and then you don't have to actually do the math. That's the lovely part of it. You don't have to really ever use these equations. You just have to understand how they work. So I think, right now that was quite a bit of theory. So I will go into some actual demonstrations. So over here, I have a demo of how shear stress works. So let's say, for instance, if I have a piece of cardboard like this and I have a scissor, if you see, you can actually, I'm sure you all have noticed with the scissors, the blades don't actually line up. They just to each other. And that is perfectly intentional, because what that means is instead of compressing it, they're actually shearing it you to cut it so effectively. Now, I'm not sure if everyone here has experienced this, but I will have to see. I'm hoping that my scissors are to work. Sometimes if you have blunt scissors and you're cutting through something that is particularly tough, this happens. It's stuck in between the blades. And this is exactly what we're looking at with shears. So what the scissor is essentially doing is that it's trying to rotate this, but because it's so close, there's barely any torque. So what happens is that just the resistances are enough that the more or less negligible, and because paper obviously tears so easily, it has a very low sort of breaking point. That's why it cuts. But of course, if you're using something that's not suited for scissors, this can very much happen. And I don't know if it's happened to you or not, but it is. So that was sort of basic understanding of your different stresses and looking at deformations from stresses. So now I think, if I may, I would like to pose a question to the audience. So I'm sure, since you guys all do robotics, I'm sure you're very familiar with the concept that a triangle is a much stronger shape than a square. But does anyone have any idea, sort of mathematically, why that's the case? What makes a triangle stronger than a square? Is there anything special about this triangle? Why is it that having sort of three sides makes it so much better? So I think I'm not sure if I'm allowed to pose questions to the audience. Are we allowed to wait for a response? Otherwise, I can just answer this here only.
Uh, I know I'm not the audience, but maybe I can answer it.
Sorry, 1 second, Stefan. I had some issues with my audio. So, all right, I guess I'll sort of explain. So it comes down to basically how the forces are once again. So let's say, for instance, if I take any 2 points of this triangle and I push on them or I pull on them, what happens is that the force along one of the beams here. So what happens is that this ends up becoming a normal force. And the only time this thing actually fails is when it buckles, and buckling is a whole other phenomena, but it actually has nothing to do with the shape itself. It just has to do with the integrity of one of these sort of tongue depressors which I've used. And as you can see, sort of no matter how I load it, it's always sort of under that load. It doesn't really bend. It's a very rigid shape. Now, with this square, I can sort of get a similar effect. Like, let's say if I'm pushing along these two sides, they're all very rigid, right? It's the same story as the triangle, but the difference here is that now I can do this and this. So because I have these opposite ends with nothing in between them, they can actually move around. And the thing is that when you're looking at structures like these, your joints are by far more likely to fail than than the structure itself. So in a lot of cases, if you want to mathematically analyze this, you can assume that these beams themselves don't deform. So a good way of analyzing it is assuming that if I take any 2 points of the beam on the beam, I can do anything to it, but those 2 points must stay the same distance away from each other. And if I apply that to all combinations of 2 points on each beam, and I apply that to all beams, I essentially get a diagram like this, where I'm not allowed to mess with the actual shape of these. So like, I'm not allowed to do this. I'm not allowed to do, bend it like that, which I'm physically not capable of doing. Do this. Whereas if I look at the triangle, there is absolutely nothing I can do to this shape. I can obviously translate it and rotate it. There's no way I can actually deform this shape while obeying those rules. And that's a really important observation. And that's where your whole concept of architecture, you sort of see these triangles everywhere. And that's also why I believe a lot of people over here would have had experience with pocketing designs. And that's why with pocketing, the most popular shape to use is a triangle, because if you have square pocketing, it does work, but you have a lot more areas for forces to sort of to basically mess up the shape of whatever object you pocketed. So that's sort of why triangles are the best when it comes to mechanical stability. So this is all good, but one thing that I'm sure a lot of you are thinking about is that, well, we don't really care if our structures bend. What we want to know is, will they break or not? And that's sort of where your stress strain diagrams come in. So over here, I have a diagram. So it's stress strain. And one thing to note is that this diagram is an engineering diagram. So it's very much made for practical purposes. So, later on when I'll talk about phenomena such as necking and all, you'll realize that the stress part doesn't actually show the stress, but I'll get to that when we reach that point. So how this diagram looks like, and I don't have a ruler, so you're gonna have to assume this is a straight line, is sort of starts off straight, then comes up, comes down, then there's an X here. So this is roughly what most diagrams look like. You have different variations for different objects, and we look at some common examples, so you can actually sort of visually see what the difference between objects is. So over here, for instance, I'm going to label a couple of points. So you have the point here, you have the point here, and you have the point here. So I think I'll start with the easiest first, which is the final point, and that is, of course, the fracture point. This is the point where your whatever you're testing breaks. There is, well, you obviously can't see what happens at a higher stress because, well, it's broken. So there's nothing you can really do. And over here is another relatively simple one, is your limit of so generally when you do a simulation, the simulation will consider that the mechanism hasn't failed if it is below its limit of elasticity. Now, I think this is, I'm not sure if you guys can see it properly, so I'll just move the camera down a bit. Just keep it like so. Just so that my text appears a little bit larger. Right here. Okay. I hope it's a bit more visible now. So over here you have, so over here you have your stress strain. And one very important thing to note is that I'm sure everyone's used to the fact that your independent variable is on the x-axis, your dependent variable is on the y-axis. But in this case, that's actually not the case. What you're really controlling is the stress, because you're essentially looking at this being, you're looking at a material being put in a machine where it's constantly being pulled or compressed or sheared. And you're looking at how measuring the strain, but you're controlling the stress. So this is sort of just the convention of the way the diagram is. And that's, unfortunately, I can't really explain why it is the way it is, but that's one thing that's important to always remember, that your stress is the dependent variable and your strain is the dependent variable. Now, then I'll get to this point. So this point is called necking. And what's interesting here is that because you're controlling the stress, you're sort of looking at things going up like this. So what's weird is that now, one point, I can even decrease the stress slightly and it'll still fracture. Isn't that weird? Shouldn't it be that I still need to increase the stress a slight bit more, but I should need to increase it for it to break? It shouldn't decrease just because it breaks. Okay, so I think I'll just take a moment here to answer some questions from chat. So yeah, if you had a shape like with more edges, like a pentagon, would it witness the same phenomenon as a square? Yeah, that is completely correct, where it really comes down to, back with this diagram, with this square, if I just sort of added an edge here, now unfortunately my pen is not the right length, but if I added an edge here, it would be rigid, it wouldn't move. I'd actually have to add an edge here and here, but essentially what I'm doing is I'm triangulating the square. And yeah, so that's the same thing. You'd sort of see with the pentagon, you would face the same issue. What's very interesting though is that with the hexagon, very often you sort of have a diagram where, let me actually just another sheet of paper so that I don't mess this one up. So with a hexagon, you would very commonly sort of see something like this. And this is also a rigid structure, because a hexagon alone is not rigid, but if you have a triangulated hexagon like this, it's an incredible rigid structure. And there are a lot of very interesting properties with hexagons, which if you're really interested in, I would highly recommend searching those up. Looking at honeycomb boards. So for instance, they're used in planes. it's a really good sort of case study into how engineers looked at different stresses and how you can sort of look at creating a design that works, that sort of allows freedom in one with one stress, but is quite rigid with other stresses. But I won't go into that now because it's a bit more complex. But I would highly recommend searching it up if you're interested. And what would be your advice to beginner engineers? I think what's really important with engineering, and that's sort of what I am trying my absolute best to do here, is that it's not about the theory. The theory really isn't that important. What's important is understanding it and putting it into practice. You could spend years sort of learning through textbooks and trying to understand sort of all of these really complex concepts. But the best way to learn is by actually putting it in practice. If you want to understand tension, actually make one of these. It's very simple. You just need a sheet where if you sort of bend, it has some resistance behind it, and then these are just some toothpicks and a ribbon. You can make this very easily. But these allow you to really just sort of see for yourself the way different, like, forces act, and the way things sort of react to how you how you work with them. So I just feel like that hands-on experience is something which I was able to get for the first time by joining my FRC team, and that's something which I think is really so important, and it's something which you really don't get as much as you should. So that would be my main advice to beginner engineers is, yeah, you need to understand this stuff, but a great way to understand the to really help yourself understand everything is through actually sort of going out and doing it. You don't obviously, with quarantine it's very difficult, but you can run simulations, you can sort of look at online resources, you can make stuff out of things you have lying around in your home. There's always a way to do hands-on activities, and I would recommend going the extra mile to find this, because that makes a huge difference. And another question is, how did you discover your passion? I think that's a really interesting question, and I would say that this is something that really worked well for me. But I feel like this also has a lot to do with the way engineering is. So for me, what worked is I like to try out a lot of things. So actually, like just a couple of years ago, I really wanted to be an astrophysicist. Just like 2-3 years ago, I really wanted to be a programmer, and now I'm sort of really interested on the engineering side of things, mechanical engineering. So for me, what was really important is just trying out everything, is going and seeing what the experience would be like. So if you're a programmer, learning learning about programming, making very basic programs is great and all, but it's important to sort of look at what you'll be doing most of the time. So anyone here who's done programming, you know that programming is like 90% debugging, and if you don't enjoy debugging, it's not a good idea to do programming. And I think that's really important. So with FRC, the experience that I got with construction, we had to make a robot so many times. When it didn't work, we just had to break the whole thing down and start all over again. We had to just be ready to spend hours, like go well into midnight to work on a robot and spend a lot of time on it. And honestly, for me, I absolutely loved that experience. That is sort of like the incredibly grindy part of working on projects like these, of doing these kinds of engineering projects. But I absolutely loved it, and that's how I knew that this was my passion. This was something that I really wanted to do, because with programming, I decided to do a project of my own, and I had to debug for that, and I really did not like it. So I think it's really important to find that thing that you'll be doing 90% of the time, and making sure you enjoy that thing. Because if you enjoy that, then you're sorted. Then it's something that you will love. So I think that's really important. Don't go for the flashy part. Go for the part you'll be doing day in, day out. So, okay, I think back to the diagram here is we were looking at sort of how the different loading conditions vary with an object. So limit of elasticity is generally considered your failing point, where if you go beyond that, you would have a permanent deformation. That's the equivalent of, let's say, obviously, if I'm designing like a water bottle, and someone by twisting it is able to permanently change the structure, that is something that is a failure in my design. So that is something which you obviously don't want to do. So that's why it's very important that people look at the limit of elasticity as failure. Then you have necking. Now, necking is a very interesting phenomenon, and it basically looks something like this. So what happens is that you start with a straight beam, but towards the center is where your stresses tend to be highest. Now, again, this goes into the way it's loaded. If, again, in a magical world with perfect loading conditions, if you were able to apply constant force, this wouldn't be an issue. But over here, you are only applying force at one point on the end. So your stress will be the greatest in the center. And what happens is that due to imperfections in the material, and there are always imperfections, you essentially have sort of this thinning towards the center. And what's really interesting is that I believe it's, I think.
I'm sorry to interrupt.
Oh, it seems that Naman is having some problems with his connection. We'll try to get him back.
Okay, yeah, sorry. My data ran out, so I had to switch back to Wi-Fi.
No problem.
Yeah, let me just change the orientation of this so it's actually viewable. All right, there we go. Okay, yeah. Hopefully the connection remains stable. So yeah, over here, we were looking at sort of necking as a process. And I wanted to sort of show it. So if you look here with this rubber band, now in focus, this is a particularly thick piece of rubber band. And if you see, as I'm pulling on it, you can sort of see here that at the center it is thinner than on the edge, and that is an example of necking. It's very subtle, it's very hard to see. It's obviously a lot more dramatic when you're doing loads with sort of very large pieces of metal, but that's basically a whole concept of necking. And what happens here is that if you look here, your cross-sectional area, your area decreases. And this is where I came back to the idea that this diagram is a lie. Because
You're having, once again, internet connection problems. You're
decreasing means your stress is actually increasing. So let me try changing my I think is better?
Kind of.
Yeah, it seems right.
All right. Okay, I'm just switching on my phone as well. All right. So yeah, sorry about that. So over here, I sort of come back to the idea that this diagram is a lie, where as the area decreases, so your stress is actually increasing. But you need to look at how do you measure stress. You're not measuring the stress, you're measuring the force. And you already know this area, but you don't know this area. You have no way to measure this area. So you're just measuring the force that you're applying divided by this area. So you cannot account for the decrease in this area. And that's why this is a very engineering diagram. If this was, anyone who is a physicist would have a problem with that because your area is decreasing, your stress is actually increasing. But for all practical purposes, you look at this as the way stress is measured. You want to look at stress as something that can be easily measured. So you're not looking at a situation where it's nearly impossible to figure out what that value is. You're just saying, forget it. We're defining stress as this cross section. It doesn't matter what happens to this one. And that's why you have this very odd behavior. And it's important to know why that happens. And it's important to know that that's how stress is defined. Now, of course, with your more complicated solvers, you don't really have to worry about things like this. They very well, they actually calculate the stress at each point. So you would look at, let's say, the stress here. Obviously, it would be a lot higher than the stress over here. So that's just sort of something that is important to know. And it comes back to that idea of just having the intuitive understanding of what this really means. So that's your whole concept of necking. And this really comes back to the idea of fracture, where you want to make sure that your loading conditions are favorable so that nothing can fracture. So then it's really important to know your materials. So for instance, if I look at a material like, let's say, your glass, or even, let's say a material that you'd be more likely to use, like polycarbonate or acrylic, you would essentially be looking at something like this as your diagram. So as you can see, there's really
It seems that you have connectivity issues. We can't hear you. Can you hear us? Naman?
sorry, my internet is
No worries.
quite bad right now.
It's okay.
I hope you guys can hear me.
Yes, we can. Oh, I think it got stuck again.
Yeah, so we're gonna wait until Naman fixes his problems. Naman, are you with us?
Can you hear me okay?
Yeah, just wait a second.
Okay.
All right. Naman, are you back with your internet, or are there still issues?
Yeah, I think, are you able to hear me?
Yes, yes.
Okay. All right. Okay, perfect. So I think, in the interest of time and my internet, I'll sort of move on to the final part, which is basically looking at and this problem, how you can really use this to analyze your robot. So I think over here, if you look at some kind of mechanism, right here. So for instance, if you have some kind of shooter, I think, is my video coming?
Yes, yes.
All right. So basically, if you have some kind of, like, let's let's say, shooter mechanism, then you would know that, let's say, for instance, you have certain loading conditions here. So you would have a certain radial force that would be there throughout. And what's important is that then you can use that analysis for your design. So you can start off with, let's say, just a supporting bracket like this, which is solid throughout. And then based on the forces, you can see, okay, where is the stress lowest? Where is the stress highest? Now you know that the areas where the stress is high are really important to your structure. So you want to keep those. But the areas where the stress is low, very close to zero, you can just remove those. And there's actually sort of an algorithm for this. It's called topology optimization. So you can actually sort of do that, and you'll roughly end up getting a structure like this. So this is sort of a great example of how you can really translate that understanding, this understanding of forces, to go from a very complicated question of, well, how do I design the support for my shooter? And you can turn that into, well, okay, these are the forces on the shooter. I can just run a simulation on this. I can see where the stresses are high, where the stresses are low. And based on that, I can cut away material to make an optimal design for the shooter. So that's sort of cases where you can really, where this analysis is really valuable. And obviously it's definitely really valuable in the validation of your design. You want to say that, let's say, maybe maybe given a storage system that I have, maybe with the it's connected to the chassis at a certain point. So maybe something like this. Then it's connected here, and you're looking at, let's say, okay, then what happens? So again, you can look at the impact. It's a bit more of a complex analysis. You'll have to look at itself. You're not looking at a constant force over time. So this is where you'll have that dynamic analysis. You'd be, okay, know, with this, is this support enough for the chassis, or will it end up buckling? Will the chassis end up bending at that point? So that these are the cases where it's really important, especially even beyond the robot, when you're going into the industry, because to test whether something will break in an unlikely situation, it's a lot better to do it in a simulation than to actually make it and actually break it, because obviously you get a lot more tries, you can get a much better analysis, and it's definitely a lot cheaper. So not just to validate designs, but also to create designs. And that is sort of where your whole, and yeah, I think that's really sort of been my main talking points for the session. If there are any questions.
I think we're all good. There don't seem to be any other things that are unclear.
Yeah. Thank you very much, Naman, for your presentation. And it was amazing to hear from you.
Thank you for having me.
Thank you all, Naman.
All right. It was really great being a part of this event. And yeah. All right. Thank you for having me. Okay.
It was really some thought-provoking stuff. Bye.
Thank you very much. Before we move on to the next presentation, I would like to remind you that if you haven't already had the chance, please check out the 24 Hours of STEM challenge at our website, 24, that's the numbers 2 and 4, hoursofstem.org. The challenge is open to all ages and groups, and 4 lucky teams will win a LEGO Mindstorms EV free kit.
activity. And I've got to say, this was hard for me to do as a last activity because it does involve Skittles, and I really like Skittles. So I had to use a lot of restraint in order not to eat them. Right now, the activity that we're about to do is all about diffusion in water and asking questions, forming hypotheses, and then seeing if our hypotheses are correct. So what we're going to use today, we're going to use Skittles. And the great thing about Skittles is that they're covered in sugar and dye, and they diffuse quickly into water. And so we'll be able to ask some questions on how they're going to diffuse and how those molecules, how those food color molecules are going to spread out through water. And then at home, to take it a step further, you can ask yourselves, what sorts of liquids can you use to see if you can increase or decrease the diffusion process. I'm going to be using water today. However, at home, you can think about using acids like lemon juice. You can think about using bases. You can think about using something with like a lot of colloids in it, like milk. You can think about using oil, something that is kind of hydrophobic. So you can play around with a lot of different experiments here. I'm going to switch to where did my mouse go? I'm going to switch to my lower feed here. There we go. And so I just did this experiment and saw that the colors started to spread out, but then got a little bit mixed up. So I'm actually going to add some more water into my second tray here. Now, the great thing about setting up these experiments is that they're so fast and you can test out a lot of different things. I used a divided plate because I wanted to try out several different experiments at once. Now here I'm just using water. However, it would be really interesting to do a side-by-side comparison where one tray was water, maybe one tray was an acid, maybe one tray was milk or something like that. Now, if you look closely, let's see. Questions aside, science is magic. How cool is that? So if you look closely, you can see the color starting to spread out really nicely, and they're making beautiful patterns. And I'm starting to already form a lot of questions. For example, why do you think green isn't mixing with brown as much? Is the mixing of colors dependent on which color is which? It would be really interesting to dive into the chemistry of these different food dyes and really study, are some compounds, do some compounds push each other away? Are some more attracted to each other? And so you can go into a lot of cool science experiments just using water and Skittles. And of course, it's just pretty too. Great. Let me bring my face back. Awesome. So that's my experiment with diffusion and Skittles.
So as you have probably heard, this was an experiment with Skittles and diffusion. And who says physics isn't awesome? With this, they added a sweet little twist to a normal, usually boring physics concept, and it's just interesting. As Aman did in his previous presentation, he got something that may sound boring on paper and made it super interesting, super entertaining to watch.
Okay, so next we have Michael Heimlich from FRC team 3132, and he will be presenting innovation and the importance of failure and stupidity in engineering. So Michael, if you are with us.
Yep, I'm here.
Okay, super. We're glad that we have you today, and whenever you're ready, you can start your presentation.
Okay, I'm gonna share my screen, so if there's any problems, please let me know.
Sure.
Okay. There we go. That's the screen that I want, I think.
It's perfect. You can see.
Is it?
Yep.
Okay, that works out great. Okay, good. I can see my little 24 hours of STEM Zoom screen seems to be in the way a little bit, but I'll work around that. That's all right. Okay, well, thanks for having me.
Thank you for
I'm
being here.
my pleasure. It's late at night in Sydney. Well, not late at night. It's 11 p.m. and that's past my bedtime. So I'll stumble and bumble my way through this. This talk is something that somebody asked me to do based on a piece of paper that I had on the side of my bookcase in my office at the university. And we'll get to that after a while. But because I'm a professor, I have to have a slide presentation. I can't talk without slides in front of me. So hopefully that'll provide some added enjoyment for the people who are watching. You don't have to look at me the whole time. And hopefully it'll provide me some guidance through this talk. But this is a bit of an open-ended talk. It's the reason why I'm giving it isn't so much because this person saw this paper on the side of my my bookcase, but I'm really excited and passionate about how people do engineering. And especially in FIRST, we oftentimes are trying to teach as mentors students about how science and engineering are done without them really knowing what science and engineering or the processes of science and engineering, how they're done. So I try to motivate the students with examples from history and fun stories. And so this talk is sort of a combination of a whole bunch of things. And I hope that some piece in here for the mentors listening will spark an idea about how you can get your students excited about the process of science and engineering. And if you're a student here, hopefully this is something that will spark your imagination as well. So here we go, and no promises on how it's going to go. So the structure for the talk is something like this. I want to talk about science and engineering sort of as two sides of the same coin. We are going to focus on engineering because when we build robots or when we, I'll say, problem solve towards a goal, oftentimes that's more engineering-ish than the science. And then I'm going to give, we'll talk about this stupidity in research idea. And this was actually the thing on the side of my bookcase, and we'll get to that around the end of the first third of the talk. And then I'll give some examples of not necessarily stupidity in research, but in engineering, we often strive for a certain outcome. And all too often in some fields, especially I use a lot of examples from aerospace, from airplanes and space flight, the failures are very public and very catastrophic. So I want to look at those mistakes, if you will, as examples and tie that back to how engineering's done. And in some of those, we'll look at what the next step was that people took after that failure, after that bit of stupidity. And then we'll close with sort of how we'll design. Now, I want to put a little bit of a disclaimer in here. I will talk about some real engineering disasters, if you will, where there was a tragic loss of life. And my intent is not to demean that or to diminish the memory of those people or what the horrors of what they went through, but rather that we do better engineering, and so that we take those tragedies and we try to save lives by doing better engineering. Now, of course, when you're building a robot for FIRST Robotics or something similar, we tend not to put people's lives at risk. We're trying to have fun, but in this talk, I'll touch on some of the things perhaps that are a bit more tragic. But hopefully, the most tragic thing that happens is that something on your robot breaks and you're able to fix it. Okay, so I have a brief video. I'm a professor at a university, and a few years ago, a few of us professors got together around this idea of something called big history, which is not that history takes 10 years or 100 years of some topic to study, that history takes millennia, and that there are well repeated things that happen inside of each millennia or millennium, if you chain them together. But the piece that they wanted me to talk about was how do we evaluate problems? And so the video, it really talks about the difference between science and engineering, or sort of what's the same about science and engineering. So here we go with the video. The big question for this segment is, what methods do engineers use to assess and solve problems when it comes to planning and building their projects? Problem solving in science and engineering can perhaps best be viewed in light of two human endeavors: a quest to understand nature and a desire to master or control it. The domain of science tends to be our seemingly never-ending quest to understand the world around us, to get to the bottom of things. Every time we gain a deeper understanding of something old, like the universe itself, or discover something new, like a previously unknown species of spider in the Galapagos Islands, we oftentimes create more new questions to be answered. The domain of engineering aims to apply this knowledge for the betterment of society. In ancient times, a knowledge of the heavens was applied to create improved agricultural systems, and today that new spider in the Galapagos may hold the secret to a cure for Alzheimer's or conquering cancer. While science and engineering are two sides of the same coin of knowledge in many instances, their practitioners go about their days in very different ways. In the case of the latter, scientists and engineers approach a problem using the scientific method. Universally accepted as the procedure for science, the scientific method creates a framework by which questions can be posed such that experiments or data can be gathered to refute the questions. The scientific method is best at disproving things, and a lot of people are rather amazed by this. Maybe an example will help. If I assert that bees are necessary to the production of apples, and I make thousands of hours of observations of bees interacting with apple trees, what have I proven? Perhaps nothing but my dedication to bees and apples. No, in fact, what I've proven is the contrapositive assertion: bees are not detrimental to the production of apples. If I truly wish to prove that bees are necessary for a bumper crop of apples, I need to create a situation where I'm testing orchards in the absence of any bees. And if I find that my apple crop drops to nil, then I can tell the world about the glorious role bees play in the life cycle of the apple pie. Using the scientific method, I create a hypothesis, a question, that can be tested by experiment. Now, to be fair, the scientific method can aid us to prove the affirmative, to conduct enough experiments under a variety of conditions to prove versus disprove something, like the mass of an electron. But it's much easier if I can phrase my hypothesis so we can disprove the negative assertion of what I want to test and immediately get our result. Finally, we also want to be very precise in the use of the scientific method. In framing a hypothesis, we can prove things in the positive, but often this requires induction, gathering a massive amount of evidence under varying conditions time and time again. We also need to be clear on separating cause and effect. An experiment can be interpreted as clearly identifying cause and effect when really it may only show that they are connected. For example, mathematicians as a group may be found to have played a lot of video games as children, but what is the cause and what is the effect? A better experiment needs to be designed to perhaps show that the skills of a mathematician lead to higher game scores and not the other way around. I don't think that parents around the world will be encouraging video games at the expense of algebra. In contrast, the engineering process aims to apply our scientific discoveries. Oftentimes, the scientific discovery is totally separate from its application. One example would be the discovery of light amplification by stimulated emission of radiation, the laser. It was decades before engineers were working on methods to send huge quantities of secure data over long distances, and it was only then that they hit upon the idea of using lasers. A counterexample is the constantly shrinking computer chip. The science research being done today necessary to engineer smaller things 5 years from now is driven by an engineering roadmap that we'd like to do our best to make happen. For apples and bees, a farmer may wish to improve the certainty that the apple crop will produce enough to pay the bills and put a little aside for her retirement. Here, the practitioner already knows what the detailed, desired outcome should be, such as the construction of a dam or the delivery of a new smartphone, and aims to create a repeatable framework that can monitor, manage, and trade off cost, benefit, and the risk or uncertainty in the outcome. What makes the engineering process so powerful is that it gives a framework for creating projects that can motivate, measure, and monitor the desired outcomes against changing, unpredictable, and sometimes unknown conditions. It cannot guarantee an outcome, but it will help you determine and then manage the trade-offs between time and resources to build that chip or bring in that apple crop. In one sense, the scientific method and the engineering process are at odds with each other because one struggles to give an answer in the affirmative and the other demands it. The scientific method has created discoveries that have led to engineered marvels that have literally changed the world in millions of ways. The engineering process has uncovered deficiencies in our knowledge, which, in turn, has created fresh questions to be answered with the scientific method. Two sides of the same coin, changing what we know of the universe around us and how we apply that knowledge. And we don't have to look at the credits, so we can just go right back into the talk. Okay, so hopefully that that gave you some insight into how we solve problems in general, and the difference between the scientific method and the engineering process, or how we engineer things. I just want to sort of summarize here a little bit. In the scientific method, there's a lot of novel things that people come up with, and we'll talk about the laser in a moment, but but certainly like a laser or the physical processes that lead to lasing or create lasing was a really novel insight in the 1950s and 1960s. But the scientific method is most easily used when we want to prove something in the negative. And hopefully that came out in the illustration with the bees. Typically, when we apply the scientific method, we're striving to find something new. One of the most popular or most talked about things, perhaps the last few years, is the connection between what people have done on the Earth and the change in our climate that we're observing, and finding the cause and the effect and the connection between those things is something that we apply the scientific method to, rather than the engineering process. In addition to finding something new, sometimes we apply the scientific method when we want to add precision to some fundamental piece of knowledge. And in the talk, it was briefly mentioned about the mass of an electron. So people continually go off and do more and more precise experiments to ascertain exactly what the mass of an electron is. Every experiment that they do has a bit of uncertainty to it, and they want to refine that and make sure that they're actually measuring in finer and finer detail what the mass of an electron is, and not capturing more and more error of their measurement system. When we apply the scientific method, we really don't care so much, although we may have a budget, we may have a schedule, we may have resources. We're not looking at managing those things. So it's not really part of the method, the cost, schedule, and resourcing of those things, which was mentioned as part of the engineering process. And we'll get to that in a little bit more detail here in a second. If we can't pose our question, if you will, or our testing, the thing we're testing, in the negative, and we want to assert something in the positive, then we have to build up a huge amount of data, almost an exhaustive amount, that shows that time and time again, under various conditions, we get the same thing to happen. So, for example, you can imagine if we wanted to assert that apples fall because of gravity, we would have to do all sorts of experiments all over the planet, not just to say that the apples fall in the orchard, but that an apple would fall anywhere because of gravity. And we would need to take out things like whether it's sunny out or whether it's nighttime, whether it's cloudy, whether it's raining, whether we have a crowd of people around, whether we have nobody around. To assert that that thing in the positive happens, we need to build up a huge amount of data. And so we would come up with a statistical argument, or we could use some inductive logic, which means by extension, or if we take this to its logical conclusion by making it infinitely bigger or infinitely smaller, that we get the same answer. Okay, there's two aspects to the engineering process, and this wasn't in the video that I showed. The first part of the the first part was here, but it's how do we harness the science that underlies whatever it is we're engineering. So what do I mean by that? Well, we talked about in the talk, the engineering process was discussed in terms of managing risk and cost and benefit, solving a societal problem. But sort of what we skipped was that with regard to any type of engineering you could think of, there's an underlying bit of science that's being applied. So if we're working in my field, which is electronics, the part of science that we're harnessing is something called Maxwell's equations. And we take Maxwell's equations, and given some problem that society wants us to solve, we apply Maxwell's equations to that problem. So we have this physics of electrical things encapsulated in Maxwell's equations, excuse me. And we apply that, and that becomes electrical engineering. Similarly, if we're writing software, the science that we're applying when we do software engineering is computer science. And if we're creating new materials, the science that we're applying for that bit of materials engineering is materials science. Mechanical engineering applies the physical sciences of how things mechanically work. And chemical engineering applies chemistry as the underlying science. So typically when we're doing engineering, we're either directly harnessing science and trying to progress something or reach some goal. And we'll get to what that exactly means in a second. But then the other part of engineering, or the engineering process, is we've already harnessed the science, and now we want to manage the process, and we want to optimize that part of the engineering process that focuses on getting to that end goal, given cost, benefit, and the resources that we have. So we want to, instead of achieve something for the first time where we're applying the science, we want to sort of manage the process and optimize it and make sure that we can do it time and time and time again very reliably. The way I think about this, in that video, the coin was spinning around quite a bit. That coin, and on one side it had Einstein, and another side it had Tesla, representing science for Einstein and Tesla for engineering. But when we get down into the engineering process, that harnessing of science to me is what Nikola Tesla was about, taking the raw ideas of Maxwell's equations and applying them in just so many amazing ways that Tesla did. That's the harnessing of the science. And his sort of alter ego, or nemesis maybe, was Thomas Edison, who was all about churning out product, making 1 million light bulbs, making 1 million phonographs. Edison was all about optimizing the process on the engineering, the process side of the engineering, and Tesla is famous for harnessing the science side. And those are also two different aspects of how we do engineering. So sort of what do I mean by this? So let's look at two examples. So you can think about the first time that the pyramids were built. We want to have some certainty in the positive versus the novelty in the negative when it came to the scientific method. So some pharaoh 5 millennia ago went to a group of guys who were the engineers for the kingdom. I don't know what the title of that role was, but he said, I want to build this amazing monument to my kingdom, and I want it to be sort of pointy at the top and have a big base, and I want it to be that sort of size and that sort of shape. And so you can imagine the engineers went to the drawing board and they came up with this stepped pyramid design. And this is one of the earliest pyramids in Egypt. And you could see the pharaoh going back to the engineers and saying, nah, that's not really what I had in mind. What I'd like is something that's like what you guys did, but I want it to have some smooth walls. And so the engineers went back to the drawing board, and they did some simple maths of the day and started building. And they started building something that had it was the right shape. It was pyramid shaped, and it had smooth walls. It wasn't stepped anymore. But then something serious happened when they got about halfway up. What started to happen was the pyramid itself started to crumble because the forces that they did not understand. This is the first time that they're like applying this scientific knowledge. We're extending the idea of how to build a step pyramid to building one of these smooth pyramids. What happened as they got to a certain height and a certain amount of mass was, or certain forces were being applied to the sides of the pyramid. The pyramid started to collapse onto itself, and they had to make the sides of the pyramid much more gradual. And so they went back to the pharaoh, or the next pharaoh, 100 years later or 200 years later, and then they said to the pharaoh, hey, what do you think of this pyramid? And the pharaoh probably said, yeah, nah, right, basic idea, but You guys just didn't get it right. So they went back to the drawing board again, and they realized, okay, we can't make the walls so sharp the sides so sharp to start with. We have to make it a bit more gradual. We have to widen out the base so there's a bigger footprint there to take all those forces. And lo and behold, I'll say on the third try, I'm sure there were a couple of other false steps in the middle here. They got it right. They had figured out how to get to that end goal. They had that certainty in the positive. In other words, the pharaoh wanted to have a pyramid that was pointy at the top and wide at the base, and had all this interior space, and was just a fantastic monument. So he knew what he wanted, but he didn't know how to get there. And they had to engineer their way there through several different failures. And along the way, they learned what it took to build the thing right the first time, to apply all that science. They created the new science of the mechanics of building structures like this. On the other side of the engineering process, so that was sort of the Tesla side. On the Edison side, we want to crank them out. We know the science. It took us a long time to build the first one. Now we want to make it inexpensive so that everyone can have one. And of course, that wasn't the case in ancient Egypt. Not everybody got a pyramid, because the amount of resources that it took was phenomenal. But fast forward to right after World War II in the United States, the returning servicemen, they wanted to have a home. They wanted to live what typically referred to as the American dream. So this guy called Levitt figured out how to make houses really, really quick, really, really inexpensively, in a way that people could afford them. And there was an awful lot of engineering that went into that, not necessarily in solving the scientific problems of making the first one, but then how do you build these things? How do you order the materials? How do you get the workforce? How do you get people to move in a timely and efficient manner? And effectively, these things all look very, very similar. You can see that as you get further back into the picture there on the right, you can see that the houses look awfully similar, almost as if they were made with a cookie cutter, one after another after another. And there's actually anecdotes of people coming home from work or a holiday and driving up to the wrong house because every house in every street looked almost exactly the same. And that was part of the secret, if you will, or the engineering of how to make these things affordable, quick, and desirable, or easy for people to move into. So that's sort of the two different parts of engineering. We have this, I don't want to say it's a tension, but when we do engineering, oftentimes we're confronted with what type of an engineering project is it? Are we pushing the boundaries of science, or are we pushing the boundaries of schedule, resources, and benefit? Now, typically, when we're building our robots, when we're teaching our kids how to build robots, there is a bit of science that we want to inject into this. But oftentimes, because of the way the first program is structured, we're more often than not doing this part 2 kind of engineering, where we're trying to teach the students how to manage resource, how to not build the best thing, but build the buildable thing, given the resources that they have. And that resource is probably the most critical one is time. Between when the game is released and when you have to be at a competition, but also there's how much risk can the students take in the problem solving phase of building the robot? How much science can be injected so that they have the capability to then transform that science into the robot? So if they're building a new sort of attachment that requires sensors and software and a bit of mechanical engineering, those things have to happen in a schedule, and the resource of knowledge and time have to be taken into account in this engineering process. So oftentimes this is what gets put first and foremost, and the teams that manage the process, manage this part of assessing what it is they can do given their budgets and given their time and given their resources, will be more successful than students who come up with some really fantastic over-the-top idea only to find that they don't have the resource, they don't have the schedule, and the time it would take them to do all the engineering of applying that science is beyond the scope of what they have in that season. Okay, so the engineering process I've sort of touched on in many different ways. There's all different models of the engineering process. This one that I'm showing, if you can see my my mouse pointer. This one over here in the upper left, this is what's called a waterfall process, and this is a traditional, or this is probably the most basic engineering process. In one sense, every time we do engineering, we use the waterfall process. I've listed or shown some of the other more progressive or newer approaches to how we look at engineering design. There's iterative methods. There's a V method here. There's something that's similar to what we call CDIO, all the way here on the left on the bottom. But regardless of which detailed way you want to break up how the season or the project is going to play out, there's certain things that all engineering processes have. There's certain elements that are common to most of them. The most important one, as mentors, I think that we want to bring to the front all the time is we want to apply the science, maths, and technology that underlies all that. We want to draw that out. In some sense, the competition or the robot working is the reward. That's really where we want to get our students to, because that's the payoff, that's the payback for all the hard work. But the motivation from our perspective as educators or mentors in general is we want them to learn something, and that's the science, maths, and technology. That competition or that robot working is the very, very well-defined endpoint. In, I'll say, real-world engineering projects, somebody defines that for you, the customer. We like to idealize that as society, especially if we're solving problems in the civic space. But if you're working inside of a company, somebody's done a marketing study that says that this is a need that people are willing to pay to be fulfilled. That's that well-defined endpoint, and it'll have specifications of what your thing needs to achieve. Now, the heartbeat, if you will, of the engineering process is this notion of repeatability. So if I'm designing a chip for the next wireless smartphone, I want to use I want to go down a path that I know is going to work, because I only have a certain amount of time, I have a certain amount of resources. So I'm going to go back and I'm probably going to use the same process I used for the chip I just designed previous to that. And I might have to modify it a little bit based on this, or differences in this well-defined endpoint, but I want to use the same process that's been proven time and time again, because that gives me the least risk to getting to this endpoint. If I know that people before me or myself and my engineering team have done this process successfully beforehand, then I'm much more likely to get success in the next thing I'm going to design. So every discipline has a process, and those processes are continually evolving as our knowledge grows, as the tools grow, as we get a better understanding of where the limits are. And we will get to the limits here shortly. Satisficing is probably a word that not a lot of you are familiar with. It's stolen from economics. And the idea of satisficing comes out of this very, very well-defined endpoint. The people in the marketing study will always tell you that their mobile phone should last for a week on a single charge. And with people playing games and talking for hours and hours. Well, the fact of the matter is that that's just not possible. The mobile phone that would do that would weigh a ton because of the size of the battery, or would have a screen the size of your pinky nail. So what we have to do is we have to balance all those well-defined endpoints, all those goals, and sort of pick the most reasonable set. And that's not always obvious at the very beginning. And as we go through this process, we will sometimes, well, most of the time, we'll winnow down those lofty goals into some more manageable ones, more realistic ones that people are willing to accept as the completed endpoint. Along the way, we're going to do a lot of conserving of our resources and cost. And there were some very good studies done by, I think the person's name, I want to say it was Capers Jones. I'm misremembering. But back in the 1970s, the US Defense Department was looking at the cost of fixing a bug in software. And it turns out if you make a mistake when you engineer something and you find that mistake sooner in your engineering process, it's a lot cheaper to fix. So we want to conserve resources because we know we're going to find bugs and mistakes later on in the process. I would imagine there are very few robots that our students build, regardless of what program we're doing, that when the robot's put together and the software's loaded and we press the button and it goes, there's probably not a robot that's been built by our students that works straight away exactly like we wanted it to. And so we have to go back and we have to iterate. And that chews into our resources. Even if it's just time, that chews into our precious resource of what time we have to get to the competition. Eureka moments. We often have to make breakthroughs, but we really want to plan for those breakthroughs, and that's a huge oxymoron. So we would like to set up an engineering process to get to that well-defined endpoint that meets all of our goals, that doesn't require any new breakthroughs. We'd just like to take things we've already done and maybe supersize them a little bit, make them a little bit better, make them a little bit quicker, but we don't want to have to go and create new technology on the critical path, if you will, of getting from when the game is announced to getting to the competition. All that being said, there still may be new things that we have to do that we've never done before, but these are the different elements of the engineering process. And when we're putting together our plan and executing it, these are the things we constantly want to come back to and assess and see where we are and manage. And that's really what the engineering process is about, managing all these things. Okay, so when we do engineering, we're actually at the nexus of this science and engineering. And so what do I mean by that? Well, I just gone through this detailed notion of engineering in two pieces. One is managing a process, one is applying science. That definition of engineering assumes the science already exists. But if the science doesn't exist and we have to go and invent the science or go find the science that we want to apply, there's no better example of that than the laser, as it turns out. I don't want to say these were a bunch of physicists, but based on the scientific knowledge that was being built up after World War II and understanding how semiconductors and transistors work, there was this notion of there's this process that we're going to call light amplification by stimulated emission of radiation. And we think that this is a physical process that should exist, but we don't know how to demonstrate that it actually does exist until we build it. So it was sort of a catch-22. So you have these guys trying to engineer a system to demonstrate a physical process. And of course, they're sort of chasing their tail because they don't exactly know what the physical process looks like. They have some indications from the science, but they have to build it into this engineering thing, and they have to go back when the engineering thing isn't working and tweak the science a little bit to match the results they're getting. So it's a very, very iterative thing. So they finally got it to work in 1960, and Charles Towns was one of the inventors of this thing, and he famously said that, okay, now that we got this thing to work and we proved that this physical effect of lasing occurs, we've created a solution looking for a problem. We have no idea, after we've done all this engineering to create or demonstrate this physical process, what the heck you do with this box that we have besides demonstrate the physical process. We can take it to museums and people could look at this coherent light source, but what the heck do you do with this thing? Well, it took 10, 15, 20 years for them to start applying it at different things. But it really wasn't until 1982, I think it was, maybe a little bit after that, that the compact disc was invented. And the laser finally had an invention, a bit of engineering that could harness its power and bring the laser into every home and make everybody familiar with lasers. Lasers are used for a whole heap of things, as you probably know. They're used for it's the backbone of the internet. It's used for welding if you have a laser welder machine. There's all sorts of things. But at the time, the laser was sort of a bit of science and engineering unto itself that had absolutely no application. And so these guys did a whole lot of work, and it's just sitting there waiting to happen. So there may be projects where your students go off and they do a whole bunch of work and they come up with this fantastic outcome, and it just sits there waiting to be used for something else. I guess don't despair. I guess they're in good company with the guys who invented the lasers. But you may want to challenge your students to go back and look at the roadmap of the laser and how that worked, how that eventually got applied, and have them think about some of the physical properties or the characteristics of the outcome and what potential things, what problems in society those outcomes could map into and solve. Okay, so we're finally at the juncture where we get to this paper that was on the side of my bookcase in my office. And the title of the paper literally was The Importance of Stupidity in Scientific Research. And this gentleman, Martin Schwartz, wrote this beautiful one-page paper. It's very accessible. You can Google this and you can download it and share it with your students. And it's a pretty easy read. There might be a couple hurdles for kids in primary school. But there are really two takeaways here that I want to share with you. The first one is that all too often, people, including researchers, think that it's intuitively obvious what it is we're looking for, or it's intuitively obvious how to go from our starting point to the ending point, regardless of whether we're doing the scientific method or the engineering process. The fact of the matter is, every time we start one of these endeavors, we're jumping off into the unknown. We don't know exactly how to get to the endpoint of building that robot. We're going to find out along the way. There's going to be ups and downs. You've always seen it every time you've done it. There's going to be new things my students need to learn or new things they could learn. And that's the element of the unknown. Even for professional researchers, right? We don't know how to get there all the time. So we want to go and, or we want to just recognize that fundamentally research is about jumping off into the unknown. So there's a whole bunch of things about the unknown that's challenging. There's, first of all, we talk about when we start a project, there's the things we know, and that's easy, and that's the path that we're going to try to take, or that's the hypothesis we're going to try to test if we're doing the scientific method. There's the things that we know that we don't know. So if your students are trying out a new sensor, you immediately know that they don't have experience with that sensor, and that's a known unknown. And they can go and do the research on it. They could look at examples of how people have applied it before, but it's something that needs to be taken on board and learned. And there may be some pitfalls and potholes along the way. It's an unknown, okay? We don't know everything about that sensor. We're going to have to learn. We have to plan to do that, and that might be, that might be one of those things where how long is a piece of string. The other thing that Martin Schwartz says, which is sort of memorable, is that when we're teaching students about how to do research, whether it's scientific method or engineering process, what we really want them to be is, what we really want to have happen is that they embrace this unknown, but we want them to do it in a productive way. We don't want them to go down the proverbial rabbit hole. We want them to get a sense of when they've gone too far and they have to cycle back down through that blind alley, get out of that blind alley and go try something else. Or they need to know that something is still worth progressing and push through that thing. And the way Martin Schwartz puts it is that we need to teach students how to be productively stupid. We need them to be naive. We need them to be adventuresome. And he captures that sense, and that's what his sense of stupid is that we don't know enough to say that we shouldn't be going down this thing. We have to go down far enough until we prove to ourselves that it's not the right way or it is the right way. So he wants us to find ways to teach students to be productively stupid and to know that this is an inherent part of every research project that we do. Okay, so the rest of the talk is sort of about some examples of where things haven't gone quite as we would have expected and what sort of things were learned from that afterwards. And one of my favorite Far Side cartoons is here, and I think hopefully that's something that we embrace. That even the smartest of us can sometimes make an innocent mistake, and sometimes we need just to step back and look at the bigger picture and see that the door is not a push door, but a pull door, and we'll get through and solve that problem and get to the endpoint that we want to be at. Okay, so some of the basics that I want to explore are at the heart of the engineering process is the process itself. And one of the classic examples of, I'll say, stupidity, again, this was a tragedy. Nobody got hurt when the Tacoma Narrows Bridge collapsed, but there's a logical sequence of events that happened from the Brooklyn Bridge, which I was just looking at today. It's expected the Brooklyn Bridge will be here in 1,000 years or 900 years because it's already been through, or I guess technically 850 years. It's been through 150 years of life, roughly. But the basic bridge is supposed to be still standing in 1,000 years because back in the early days of building suspension bridges, and at the time the Brooklyn Bridge was the longest suspension bridge, and probably within the first dozen or so suspension bridges of its time, the enabling technology that was created that allowed this to happen was the steel wire that the Roebling family invented, or they came up with a process of making very strong steel wire in a very inexpensive way, and they were able to build very, very long bridges. The Brooklyn Bridge being probably the pinnacle of the ones they created for some time after that. But they totally over-engineered this bridge because they didn't have the CAD tools. They didn't have finite element analysis. They understood the statics and dynamics of forces, but they didn't have the tools to do the detailed calculations of exactly what force would be on the bridge and exactly how strong the materials would have to be. So they over-engineered the bridge to the point where this thing's going to last for 1,000 years. Well, over time, people took the design of the Brooklyn Bridge and they simplified it, and they made it more economical and more cost effective and easier to build. The Brooklyn Bridge took something like 20 years to build. They started being able to build bridges in 2 or 3 years with a tenth of the material. The Tacoma Narrows Bridge is the logical progression of those constantly repeatable processes of engineering bridges, where they took more and more material out of the bridge and they used less and less people, or less, I guess, less intense manufacturing to put the bridge together. And what happened with the Tacoma Narrows Bridge was that they took so much mass out of the span itself that instead of it being a sturdy platform, it actually became a wing, a lifting body. And when the wind blew just the right way up the river channel there, the bridge deck took off like an airplane wing. And it turned out that not only was that surface a wing, but it also had a resonant frequency that had to do, was somehow related with the way the wind was gusting, and the whole thing started oscillating and it tore itself apart. So we have a process, that repeatable process, driven by that desire in the engineering process to be conservative in terms of cost and benefit. People were taking the mass out of the bridge, and we wound up with something that was under-engineered, and it collapsed. So people went back to the drawing board and they had to stiffen up the bridge deck and put in stiffening members so that the thing would not oscillate and would not act as a wing. Okay, moving on to some of the other basics. We talked about the resources that get used in the engineering process. So I want to talk a little bit about materials and manufacturing. Many of you know the 787 or the A380 as the workhorses of intercontinental travel today. Well, the original intercontinental jet for commercial air flight was not a Boeing product, although Boeing existed at the time. It was not an Airbus product. Airbus didn't even exist back then, but it was from a company in the UK called de Havilland, and they created the first successful commercial airliner called the Comet. And this plane would go up to the same altitudes our planes today go up to, and they would land, and they'd go up and they'd land and go up and down, up and down, up and down, and the cabin would be pressurized. And unlike a military aircraft, which were doing the same things, commercial jets would go up 10 or 20 or 100 times more frequently than the military jets. And what finally happened was the Comet jets started falling out of the sky, and when they would crash, unfortunately, there's a tremendous loss of life, but they started to see this consistent pattern where the plane literally was ripped apart in the manner that I'm showing here in the middle slide. What was happening was they had discovered something called material failure. And what they didn't realize was that when you take a piece of metal and you machine it so that it has sharp corners, and I don't know if you can see in the first photo here on the left, the windows on the Comet, the original Comet, were very square. And you can sort of see it here in the middle picture. The windows are somewhat squarish, and the way they'd attach to the fuselage was along a flat line. Well, when you machine materials and you start to stress them repeatedly, that's called metal fatigue. There's things inside the materials called metal defects that actually strengthen the material and make it stronger. But what happens is over time, those defects will move or migrate inside the metal, and they'll find the point of highest There's a internal forces inside the metal, but they'll find the places where those forces are highest and they'll get stuck there, and those are at the corners. And so what was happening was all these fatigue points were accumulating at these sharp edges, and finally they would just fail. The material would become so brittle, and the material, the side of the plane would explode out and it would crash. When they finally made the corrections here in the later versions of the Comet, you can see that the windows are much more circular. By that time, unfortunately, all the science that they did to solve this problem, to basically create the science of material science back in the 1950s, and metal failure or metal failure and metal fatigue, by that point in time, Boeing had also been watching the science, and they had come out with the 707. And today we don't even hear about the de Havilland Aircraft Corporation because this literally ruined them, even though they went off and solved this problem. So oftentimes when we build things, we will pick the wrong materials, and we may pick the wrong manufacturing process. We really need to think about what materials and processes we're using. And if we see failures, we need to learn the lesson of the Comet and go back and look at, well, what's causing this failure? Is it in the manufacturing? Is it in the material? Is it in something that we're doing together with those things? Oftentimes our students would love to do things like carbon fiber, and that might not be accessible to you because of the environmental hazards associated with that, or you may not just have the vacuum bag technology available, or yeah, you just have to go with some other way. But I see a lot of teams trying to do carbon fiber stuff, and that's sometimes not within reach of people. And then there's my old favorite schedule, which I hammered on a little bit a while ago. The Spruce Goose was a plane that Howard Hughes convinced the US government he could build in 2 years. He was going to deliver 3 aircraft in 1944 to act as a way to transport troops and materiel very quickly from the US over to Europe. It had a range that in one go could get 2 Sherman tanks from New York to London. Yeah, he said, we'll deliver 3 of them for you by 1944. 1947, they still haven't gotten the first one done. It was a very complex machine. You could see it had 8 propellers, 8 engines on it. It was huge. It's the size of a 747 or an A380. And this thing was being built out of wood in 1942. So they had no idea. No one had ever sort of done this size of vehicle before. They had no idea what sort of problems they would have in terms of resourcing it. It wasn't made of spruce, by the way. It was made of birch. And the birch was sort of a laminated material that was made in Wisconsin, of all places. And so the engineering of those materials was just way beyond what they had imagined. And this thing took basically 3 times longer than they thought to get up and running. So oftentimes we will not understand what it takes to resource our projects with our students, and we'll just lose control of the schedule and we won't get to that endpoint. So we really need to be very mindful of sort of again, what it is we know, what it is we know we don't know, and make some allowances for the unknowns to get the schedule in place. Okay, the missing link. Looks like I have an animation problem here. I apologize for that. In the early 1990s, on the heels of the success of I'll say the first home personal computer, the Apple II, Apple went off and did the Lisa, and that was sort of a failure. And then they did the Mac, and that was a success. They decided they wanted to shrink the Mac down into a tablet, so they invented something called the Newton. And the Newton had basically all the features of the iPad, except for one fatal flaw. Well, besides the battery, this thing was the size of a brick, so that you could operate it for 4 to 6 hours. You had to plug it in and download everything over a wire. It couldn't go with you. You had to stay where it was, basically. And of course, the technology that most of you don't know about the Newton, it was a fantastic leap forward in personal computing, because it basically was an iPad 10 or 15 years before we had iPads. But the fatal flaw was a missing link in the engineering. It was a critical system, this ability to download and upload data. In other words, how do we get to the rest of the world? That required this wire thing. So it totally took away from the lightweight personal aspect of this and the mobility that this implied. And it wasn't until, I'll say, roughly a decade later that here in Australia, CSIRO invented Wi-Fi, some folks that I've had the opportunity to work with in terms of the science of it, John O'Sullivan, and then the engineering of it. Dave Skellern and Neil Westby were the leaders of the first team at Macquarie University to put together a chipset that actually made Wi-Fi work. Now that that missing link was in place in the early 2000s, it wasn't but a few years later that Newton was resurrected, combined with Wi-Fi technology, and boom, you have the iPad and a whole new revolution in personal computing. So sometimes we find that we solve a whole bunch of problems only to create another problem for ourselves, in this case, in terms of mobility, that requires us to go back and do something fundamentally new in terms of the science.
I'm sorry to interrupt, but we are very close to the finishing, and we have a lot of questions from our YouTube stream. And if you'd like to answer a couple of them. Yeah,
we can do that. I just want to make two other comments before we do this. Okay, so I think when it comes to engineering, there's two things you want to be aware of. One is what I call PhD-osis, or don't let the haters win. When we sit down and we plan an engineering project, there's always somebody who's going to say, you know, we tried that 2 or 3 years ago and it didn't work, and they want to shoot down the idea. You have to fight, and I don't mean that in a negative way. You have to support new ideas, and you have to give them a go. It's really easy for people to say that won't work. It's really easy for people to say that. You have to give people space and let them try again, because on nearly every engineering project I've ever worked on where there's been a tremendous breakthrough, we came up with all the reasons for why it didn't work, but we still tried it anyway. And if we had listened to ourselves, it would have been too easy to convince ourselves we couldn't do something. So really, you need to think very critically about naysayers and these reasons, and see if there's easy ways to push forward anyway. The other one is there's oftentimes I hear people say somebody says something like, oh yeah, we're going to have to do that. That's really hard. And somebody else says, oh, no, that's really easy. All you got to do is, and whenever anybody says all you got to do is, that should send warning flags up. It's not going to be all you got to do. There's going to be a little bit more. There always is. It's one of those sort of Murphy's laws of engineering. But finally, doing engineering, the engineering process, you should find a lot of people who have a passion for science and engineering like yourselves, and have fun, just like the Big Bang Theory folks. So sorry for going over, but I'll take some of those questions now.
No problem, don't worry. The first question would be, what would be your advice to people who fear failure?
I think you have to embrace failure. Engineering's an iterative process. So pick something that you could fail fast on, and figure out those things that I talked about before. Know what, put down as a helper. What do you know? Put down at what are the unknown things that you already know about that you're going to have to look at more deeply. And those are the things that you should attempt to fail fast on. And hopefully you'll get over your fear of failure by being able to succeed after a few very quick failures.
Another one would be, do you have another personal example of failure?
A personal example of failure. Gosh. Look, I've been on first teams where we had a pretty good understanding of what we wanted to do for the end goal. We knew what the resourcing was, and we consistently did not meet the schedule and failed. So I guess the lesson that I got from that is commitment to the schedule and the resourcing. Apart from all the science, apart from all the engineering, apart from all the maths, you need to really manage that schedule and get people to commit to doing it. So for the first teams, if you're going to meet 3 times a week, for 3 hours at every meeting, you better plan on doing that. Because your schedule is going to be based on that. So without that level of commitment, I guess you're failing right from the start. So that's one of my personal failure experiences.
Yeah, so it's what I get is it's more important to be really concise and productive when you meet.
Yeah,
So
I think, look, I think we all want to have successful seasons, and one of the things that we get so enamored with the science and technology, or we let our kids get so enamored with the science and technology that we don't support them to that end point. And as I said at the top of the talk, the end point is the most important thing. It's where the kids get the payoff. So we as the mentors really need to manage the engineering process so they can get to that end point. And we don't want to throttle their enthusiasm, but we have to sort of keep it contained so that we can make sure they resource the project properly and they do get to the end point.
yeah, amazing. And
Yeah.
for our last question, is there a
Yeah.
cultural bias in failure? Is failure easier in some places rather than the
Oh,
others?
absolutely, absolutely. I talk to a lot of people in government about innovation and entrepreneurship, and everybody constantly says, "What all we want is we want to have another Silicon Valley." I say, "You don't understand. You don't have the culture for Silicon Valley. Silicon Valley was founded by a bunch of hippies who weren't afraid of failing, and that culture of failure was embedded in them from 20 or 30 years before that." So yeah, it is a cultural thing. Here in Australia, we have some fantastic engineers. As you could tell, maybe from my accent, I'm not born in Australia. Australian engineers are fantastic. They're so risk averse that they will have a airtight engineering process to get to that endpoint, but they're very risk averse. They won't take a lot of risk onto a project, and so the endpoints that they get to are much more progressive than what you'd see coming out of an engineering team, perhaps out of Silicon Valley. And then you could transplant that into any culture. There's cultures that are absolutely failure abhorrent. You can, I guess you can go back to, let's say, Nazi Germany, right? If you failed in Nazi Germany or communist Russia, you may not have wanted to own up to those failures for obvious reasons. So yeah, I think the ability to do good engineering is very culturally biased. And I'm not saying that Silicon Valley is the best way, by no means, because Silicon Valley is very profit driven, and there are places where there's a lot of really good engineering being done in the social space to solve real problems that society is grappling with. So yeah, there's definitely a cultural bias, and you have to be aware of that in your company, in your if you're a professional engineer in your school, what some of the cultural biases are. In terms of maybe putting in the extra hours. If you're an extracurricular activity and your school is very academically focused, there may not be room for those extra hours because the students are expected to study. And that would be a cultural bias in this engineering process management.
Well, thank you very much for your presentation. Personally, I can say I truly enjoyed it. Ever since I saw the title of the presentation, I was looking forward. Yeah, I was really looking forward to it. So
Yeah.
thank you very much for being here. It was
Yeah, you're very welcome. And maybe sometime I could get through all the slides, but that's what the problem of being a professor. You always make too many slides.
Yeah. Thank you very much.
Thank you very much. It was a pleasure being here.
Same here. Thank you very much.
Bye.
Bye.
Today's event wouldn't be possible without all of our incredible sponsors. We want to thank you, Boeing, Google, and Macquarie University for their generous support.
Now, what we've been exploring more recently is what if we print our own Lego pieces? The project that prompted this was we needed to attach a marker to a driving robot base. Let me show you how we did it. So the tools we used Tinkercad. We used another website called Thingiverse, like a universe of things. And then we used the 3D printer to print out the final product. First, we went into Thingiverse and we didn't want to ourselves reinvent the the geometry of the Lego holes, we anticipated that others had done that before. So we searched Lego beam, and sure enough, others had created some Lego beams, and let's try this one here. I don't actually need to print this beam itself. Instead, what I need to do is bring those holes into Tinkercad in order to make the marker holder itself, because that's the part I'm going to have to use Tinkercad for. So let me go into the files, and I'm going to just copy the address, because that's actually all I need. Now I switch over to Tinkercad. Could this be done in other CAD programs? Absolutely. So here we're just doing it in Tinkercad because that's what I am familiar with, and it's free. And I've got my blank canvas. Well, what I want to do is add my Lego as if I could take this and just put it right down on the blank canvas. Import from a website, and that was the website that I had from Thingiverse. There's my beam. Okay, so I've got that Lego beam in there, and what I need to do is figure out how can I create a shape to grab onto this marker that's attached to those Lego holes. Like my hands, if I grab on, what if I just sort of think of a U shape? I'll be honest, in the interest of time, I'm going to skip some steps related to measuring this marker to make sure it fits into this particular holder. I just want to show our viewers this process of attaching anything to the Lego beam that serves your purpose. So I'm going to bring a cylinder out here, and then I'm going to bring a second cylinder out. I'm going to shrink this. The neat thing is in Tinkercad I can make one shape a hole to cut it out of a second shape. Let me group them together. And in the case here of my Lego holder, I do need it to kind of be able to sort of come out and as if it's to grab. But what I'm not showing you is whether this holds a wide marker or holds a skinny marker. I just want to show, in this case here, how I've attached to the Lego beam, and then how I've actually shortened the Lego beam. So if I bring that down there, that Lego holder is just on the edge of this beam, and when we combine the two shapes together, they'll be fused and printed as one. But I've got one more trick up my sleeve, because I don't need all the holes in this Lego beam. In fact, I just need a couple. So I'm going to cut those off. So I group that. Bye-bye. And I'll zoom out here. And I want to cut those off. Group them together. And I've cut it. Now again, interest of time, I'm not worried about smoothing out those edges or anything. So I will fuse them so that it's now one piece, and I've just invented a piece to hold a marker. So one last trick though. Okay, so I have the holes facing up. What if I want the holes facing the side? Let me ungroup. So if I wanted to flip these 90 degrees, like so, and I group them together, and again, we've just invented our own Lego piece to hold a marker. So we've previously printed the design that works with this marker, and if I clip that on there, we can see that fits. My pegs in and attach it to my Lego beam. So I now have a marker holder that I can attach to, say, a robot that drives around. If you want to see more about the robot base and the project where we're drawing on a surface while we're programming the robot, please click on the video that's linked below. Let's go to the whiteboard and point out a few more ideas you can try on your own. In this
All right, so this has been 3D printing Lego attachments. in which, of course, you can use your creativity and everyone else is using Thingiverse to kind of let your mind be free and use the power of Lego to create different robots.
Now let's move on. We have Chris from FRC team 1073, and he will be presenting a portable web-based scouting solution. So Chris, whenever you're ready, you can start. Do you hear us?
Can you hear us, Chris?
So, muted. Yep. And okay, I will start the video here, and I will share my screen. And I want to share the whole screen. Where's that? Right there. Share. Sorry. And okay, and I will start this presentation. Okay. Greetings, FIRST community. My name is Chris Holmes. I am a mentor with 1073, and today I want to talk about scouting again. Scouting. Let's play with the game. Let's play the games, right? So we're going to talk about a specific match scouting solution that we came up with at FRC 1073, and we think it's got a lot of usefulness and value, and we want to share it with other people who might be interested in scouting. First off, if you are new to scouting or need some scouting tips, is my window here is kind of in the way, so I'm just going to move it. Let's see if I can get it. I don't know if. All right. I just need to move the people viewer. Okay. So I highly recommend the scouting system development presentation that was given 11 hours ago on the mass stream by Ethan and Kevin from the Citrus Circuits. They give a great overview on all the aspects of scouting, from kickoff and even before kickoff through data collection and analysis, using that data to predict. They gave great tips on, they create a strategy rules test to make sure their team is all set and ready to go. They talk about having a minimal scouting data set and how that contributes to the importance of data accuracy. It's a really good presentation. I recommend if you didn't catch it, to catch up on, try and find their presentation and watch it again. They also, like I said, they also talk about match strategy. So using the scouting data that you have, either from that event or from previous events, to kind of decide how you and your alliance are going to match up and compete against your opposing alliance, using the scouting data to try and do some prediction, total up the OPRs of the 3 robots and see how that matches up against the OPR of the other robots. And then finally, the basic of scouting data is really to help with your pick list, to decide, okay, after we've watched all these matches, who are the 2 other robots that we would work best with, and try to advocate for building that alliance. That's really what the scouting data, kind of its key value at any event. So they talk about that, and that aligns with 1073's goals in scouting as well. These are all the things. So it was great watching their presentation and just nodding our heads as we watched them. And finally, one of the things that they pointed out is data transfer. However your users are collecting the data, how do you get it to a central location? That's a challenge at all FRC events that is real. We've been to some events, I'm sure you guys have too, where cell service is shaky. Never mind trying to jump onto the Wi-Fi with hundreds of other students at the event and competitors at the event. So having your scouters collect the data is one thing, but then aggregating it to a central location can be the real challenge. That was kind of the motivation behind the solution that we came up with today that we'll talk about. So our solution that we're presenting is, first off, portable. We know we need to bring it to events. And really the solution to the data challenge is a wired network. So we decided a wired network is the most reliable way. So we basically build ourselves a little mini internet to take with us. And so, yes, the solution needed to be portable. We need to be able to set it up in the stands and use it. And we carry it around in one of those metal suitcases that in the movies you see are usually filled with money. Ours isn't filled with money. It needed to be low cost and flexible. So we hope that's appealing to a lot of teams who are starting out with scouting. It's basically a Raspberry Pi web server. And then over that wired network, we have our clients, which are tablets, but can be laptops, can be Chromebooks. Because the solution is so we decided, okay, we're going to have a cabled wired network, then we might as well just make a central web server, and the clients just need web browsers. The clients just need to be able to plug into a cable, and they need to be able to have a browser. And that's very common. Every laptop you buy is going to have a browser. Tablets are going to have browsers. The tricky part, the key is just making sure you have that ability to connect to a wired network. And I'll talk about that in a little bit. So having constraints, having minimal constraints like that means there's several options that you can use. You can get a Raspberry Pi like we did, which is very low cost, or you could use a laptop if you already have a laptop to be your web server. This solution will also introduce command line Ubuntu Linux. So that's what we're going to build our web server with. We're going to use the Ubuntu Linux operating system. It's free, and it's very popular in the industry. I'm a software developer. I didn't really introduce myself, but I'm a software developer with HPE. So I've been in software for 20 years plus now. Ubuntu Linux today is what they're using for AI. It's very popular as an AI platform. A lot of companies, a lot of industries are using Ubuntu Linux, as well as just people at home and developers. So probably many of you may already be familiar with Ubuntu Linux. We're going to use the Apache web server for our web server. It serves roughly a third, one out of every 3 websites that you visit might be served by an Apache web server. Apple.com uses Apache, for example, Craigslist. So we're using industry standard tools that have been well tested. We don't need to worry about that. And it's good to have that skill to say that you're familiar with the Apache web server on your resume. So. And we're going to discuss basic networking concepts with this solution. So you're going to get familiar with, setting up this wired network and needing to serve IP addresses or configure IP addresses. So all of these skills we feel are useful to anybody interested in tech and in STEM. So we're just making use of those skills and teaching them as well. And finally, for software developers, all of our software is now web pages. So teaching HTML, which is really just a formatting, it's hypertext markup language is what HTML stands for. And it's really just saying, take these words and make them big, or put them over here, or take this content and create a table out of it. So it's just tags on either side of your sentence or your content that tells the browser how to display it. So this solution uses HTML, and for developers that want to enhance and develop this solution, add enhancements to it, make changes, you'll learn HTML, which is very valuable in the industry for web development. And it also teaches scripting. So the current application is developed using Perl scripting language, but really any scripting language can be used. If your team is more familiar with Python, feel free. You can rewrite the whole app in Python if you wanted, or you could just add your changes in Python if you're familiar with another language. As long as it can print HTML to the screen, you can use it. So the solution is, again, really flexible, really adaptable to the skill set of your team. And finally, it teaches GUI design. Anybody that's developing an app for users is going to need good GUI design. And again, that's where I'd refer back to Ethan and Kevin, where they did a great job talking about, you need your scouters to provide you accurate data, and you need them looking at the match. And not down at the app saying, oh, where do I count the power cells? So in developing this solution, it gives your team a chance to work out the kinks in a good GUI design. Apple has solved has solved good GUI design. A lot of people like Apple products. Android, anybody's developing apps on phones are going to run into this same challenge: is how do you make a good intuitive design? In the industry, there's a 90-second rule. If a new user can't figure out your app in 90 seconds, there's a good chance they're just going to remove it and add another app. So that this sort of follows along with that. You're going to want your scouters to be able to pick up and know how to enter good information into your app, so that they're more focused on the match and less focused on using your scouting tool. Okay, so that's it for slides. Let me jump off of slides here and let's go to the website. So everything that I'm going to present, our solution, is all documented at our team website. So if you go to frc1073.org, under resources, there's the scouting app tab. And this is broken up into 3 sections, and we'll dive into each one. The first section is building that Raspberry Pi web server. That's the central core of the solution, is having a web server on a Raspberry Pi. So we'll go over the few steps here to have that. Once you have that, then the second section is about getting that Raspberry Pi ready for competition. So downloading the scouting app from GitHub, installing it, configuring DHCP. So that is DHCP is distributed host. Oh, I forgot. We'll find it on the web page, but it is what your router is serving at your home to give all your devices IP addresses. It is what your router at school is running to give out the IP addresses at school, at the coffee shop. And so if we're going to build our private network to take into the stands at an event, we set up DHCP on the web server so that it becomes the central IP provider to anybody who cables up to that network. So we set that up, and again, that's an industry standard software that's used everywhere. And then finally, this section talks about assembling the hardware, and we're going to jump into that next so that I can give you a visual on how our solution looks. But then finally, the last section on this page is for developers. So this is going to go over basic HTML, and it's really going to and move into scripting. And the goal of this section is to teach you the techniques. How do you create a web page for a scouter to click a button that says they just shot a power cell, and to have the web page store that information and then create a new web page with the updated number, so that the scouter can say, okay, you got it. And then he can keep clicking and pushing buttons we're making web pages that collect that data, store that data, and that eventually write that data to a central database so that that data can then be analyzed. And so this section is about teaching that technique of how to make a web page that collects data, takes input from users, stores it. And at the end of the instructions, we create a couple of just little simple web pages, makes a tic-tac-toe board, makes a counter. And once you've gone through this, then the hope is now you're ready to dive into that source code from GitHub and begin modifying and enhancing the scouting app to make changes that you might like to make. So let's go back and take a look at our solution from a hardware perspective. So there's a little inventory list, but here's the solution. Okay, so we'll start at the top. I just want to make sure nobody's wondering. I hope the connection's well and I'm not talking to myself. Okay. Okay, So we'll start from the power. So this little red and black device is our power converter. A lot of you are probably familiar with these. The red plug plugs into a robot battery, and there's 2 outlets. And coming out of the one outlet here is a power cord to our Raspberry Pi server. So there is the complete and configured and ready to go Raspberry Pi server. Coming out of the Raspberry Pi server is a power line to an 8-port switch. This could be plugged into the other outlet on the converter, but we actually like to keep that open for laptops. So, and this switch was powered by a USB plug, so we were able to just plug it right into the Raspberry Pi and sort of piggyback on that. And the other cable coming out of the Raspberry Pi is the Ethernet cable, which is plugging in to the switch. And then coming out of 6 other ports on the 8-port switch are the cables that are going off to the various tablets. And each one, the Ethernet cable, is eventually plugging into this adapter here, which takes an RJ45 plug and converts the communication wires to micro USB, which plugs into our tablet. And we've got these little black Velcro strips on these tablets so they can stick to the back of the tablet, because this is the critical plug. Anybody who's had a phone with micro USB or a tablet, you know those plugs can wear out, and certainly at competitions, they could take a beating. So we would rather this adapter take the brunt of moving, passing tablets around rather than this connector, because we don't want to keep replacing tablets. But that's it. And then we have 6 tablets here in the picture. Now, these tablets, as we mentioned, could be laptops. And as long as the laptops have an RJ45 connector, you can just plug this in without the adapter. Some newer laptops don't have RJ45, but they'll have USB. And I'm sure you can find an RJ45 to USB adapter for your laptop. So really, you can plug, your scouters can be using any device in this solution. And in fact, the Raspberry Pi could itself be a laptop if needed, as long as it's hosting Ubuntu. Okay, and that's it. That's the essence of our solution here from a hardware standpoint. So we'll go over the steps to standing up this Raspberry Pi real quick. Let me just do a quick time check, because I also want to make sure we have time to go over the app. I want to show you the app as well. These steps are really designed to just follow them step by step, and you will have, if you have the hardware ready to go, these steps will get you up and running. And you can use this scouting solution. Everything is freely available, and all the instructions are hopefully accurate and correct. So the first step is Raspberry Pi. And I'm not going to go over these in detail. Basically, I point you to the Ubuntu page for installing Raspberry Pi. The instructions are very straightforward. So follow their instructions to get Ubuntu installed on the micro SD card, and then you plug the micro SD card into the Raspberry Pi and power it up. And they provide instructions on connecting it to your network. I covered some here as an example. And then I also talk about the software that you'll use to log into the Raspberry Pi. So being able to access computers remotely is huge, I'll say, in the industry, especially now in a pandemic. Being able to log in. This is how I do my job every day. I work from home, and I log into systems in Germany, in Houston, in Michigan, all through a terminal like this. So this type of skill set is very common in the tech world today. People that perform IT service and maintenance, maintain a lab for a company, they're logging in remotely using tools like this. And in fact, if you're watching the news lately, there's been the solar wind hack from Russian hackers, which was likely done from command line like this. So this is a popular way to be able to enter the internet and log into various systems. So here I have the Raspberry Pi, down in another room in my house, and I can sit here in my recliner, bring up my laptop and connect to the Raspberry Pi and work on it. And you guys will be able to too. And that's actually the next step, is just some quick Linux tutorials, some commands to run once you're logged in like that. So that'll go over the various commands and show you some output. And then the next step is, speaking of hackers, how do I update my Ubuntu environment to get all the latest security fixes and all the latest bug fixes? So this recommends, running the upgrade steps to download the latest patches. And it also talks about a text editor, because now that you're in this terminal window, how am I going to edit files? How am I going to make changes on the system? And this introduces the Emacs app and creates a little Hello Dean program. So to show you what you can use to start editing files when you're logged in remotely like that. And then the next step is, now that you're connected and your Raspberry Pi running Ubuntu is all up to date with the latest software, the first step is we need to give it an IP address. So web addresses all have IP addresses static, so they can't move around or you won't be able to find them. When your laptop connects to your router, it gets one IP address, and then when you power it down, go to bed, wake up in the morning, power it back on, it might get a different IP address, depending on who else has come into the network and requested an IP address. Printers, for example, those who have printers at home know configuring a static IP address is a great way to avoid losing access to the printer when the printer loses power. Say if you have a power outage, or if you just had to move the printer and you unplugged it and plugged it back in, if it gets a different IP address, then your laptop, which was working with the printer because it was configured, it found the printer with a certain IP. Now that IP is old, and your laptop can no longer find the printer, and you've got to delete the printer and re-add the printer. That's all because that IP address has moved. So configuring a static IP address is how you avoid that headache. And the same for the Raspberry Pi web server. You're going to want to give it an IP address where you can always know how to get to it. So the instructions here cover that. Once it has an IP address, then the next step is to install a web server. So install that Apache web server, and it's really just one command here, as long as the Raspberry Pi is connected to the internet there. One command, and you've got Apache on it. And I provide some description here on how a web server works. Basically, it's got a directory where if you put a file there and somebody asks for it, it's going to give it. And that's great. That's just the basis of every web server. Give the file when asked. But we need to make interactive web pages. So what's going to happen is, instead of having the server just provide a file, we're going to give it the name of a program, and it needs to run that program, and that program will produce the output, which becomes the file that gets sent. So we need to configure the Apache web server for this CGI support, or Common Gateway Interface. And that's the API that tells Apache, you're asking for a CGI program, I need to go get it, and I'll give that to you. So that's covered here, and the instructions to configure CGI is right here. And once you get that enabled and configured, now you have a web server ready for the Scouting app. So the next steps would be to install the Scouting app. Or at this point, you can go down to the development section and start running through some of the examples in the development page. So software developers, once you've got the Raspberry Pi to this point, go down there and start going through the steps and start learning how to develop your own web pages. And that's kind of fun to have in your home as your own web server, and you can create your own content, and it's pretty cool. Okay, so the GitHub location is right here. Click on that, takes you right to GitHub. The the repository is called Web Scout, and you'll see there's a 2019 location and a 2020 location. So it's got Destination Deep Space, which was the year we first developed. That app is here, and also the 2020 Infinite Recharge is here as well. Okay, we'll go back. So you do a git clone. You can pull that right from the web right to the Raspberry Pi. The Raspberry Pi has Git by default on it. Excuse me. And now you have the software on the app. You copy the software into the server location where you've configured Apache to look for these programs and look for these web pages. Once you copy them in, then your scouting app is up and ready. And the last step after that is configuring DHCP. So like we said, if you're going to create our own private mini internet in the scouting stands, we set up the Raspberry Pi to give out IP addresses to anybody that plugs in. And that's handy not only for the tablets and the laptops that are going to connect for scouting, but also like what Ethan and Kevin talked about, we typically have a runner that communicates, that gets data from the stands and takes them down to our drive coach and our strategy team. And so they may come up with their laptop, plug in, grab the data, run down to the drive team, and go over the data, look at it, decide how they want to approach the next upcoming match. So being able to just plug in and not have to worry about your network is very handy. So having DHCP set up on the Raspberry Pi is very useful there. Once you do that, you're ready to go. Pack up your suitcase and take it to an event. Definitely practice. Test that out when you provide your testing to your scouters. Set it up on your table and let your scouters play. So let's take a look at this app. So you plug in, and so my static IP address for my Raspberry Pi is 192.168.1.73. And when I go there, I get this page. And for developers, we can take a quick look at the page source. That's all it is. So HTML are just these tags. You can see FRC 1073 Scouting App. That's up in the title here. There's the Start Scouting link. Here's the Head Scouting link. The Head Scout is going to take me to this admin.html page. The Start Scouting is going to run this CGI bin index.cgi program. And so you'll see how the program is going to run. And then there's just a bunch of line breaks, and that's just to space out the words. So that's simple HTML in a nutshell. You can edit a file and add whatever tags you want. And I could have made the background blue. I could have made the words bigger. I could have added pictures. All of that is in the tutorial section below. But so your scouters will go to Start Scouting link. But if you first get to a match, your head scouter is going to want to go here. And what he's going to want to do, or she, is configure an event. So if you can get a hold of an internet connection, then as soon as the match is announced and made available, it typically is also uploaded to Blue Alliance. And that's the easiest way. The first step you need to do is load the match into your scouting app. So we have instructions here. If you can get to an internet connection, go to the Blue Alliance, select the event, right click on the match schedule web page and select view page source. So just like I did, you want to see this content from the match schedule. Don't copy the match schedule itself. We want this content because this HTML provides structure and helps our program find qual 1 and the 3 and the 6 teams that are going to compete, qual 2 and the 6 teams that are going to compete. So you go to here, the instructions say, view the page source. On the page source view, select all of it and copy it. So you're just going to do Control A and Control C. Now you've got the match schedule on your clipboard. Now you disconnect from the internet, however you did that, and plug into your private network here. Connect to the scouting app, come to here, select in here, and actually I can do it here. Copy, and then come down here and paste. And that's what you want. You know, obviously you don't want that page, but you want the match schedule content copied into this text. Now all I have to do is hit upload event, and this content, the program behind it, you can't see it, but when you hover over, I guess even hovering over, when you click upload event, it's going to run a program that is going to parse all that HTML, find the matches, and put the match together. If you can't get an internet connection, then you've got to manually type in your matches. And usually you only have to type in the matches for the first day if you're really nowhere near any kind of internet. So get that match schedule sheet, sit down and type it in. And the key is if you match the year up here and the venue with the two keywords that the Blue Alliance is gonna use to designate the event, then you only have to type in the first day. And then when you go home or back to your hotel at night, you can get on the internet, go to Blue Alliance, download the match, and load it, and it will fill out the whole match schedule. Now, the tricky part here is you've got to sit and type each individual team in here. And again, referring back to Ethan and Kevin's excellent presentation, data accuracy is important here, right? If you put a team that isn't at the event, then somebody's going to be scouting a team that doesn't exist or isn't actually at the event. So, and actually for developers, this is an interesting spot where you could add some code here. So you know the teams that are going to an event ahead of time. So you could enhance this software to be able to provide a valid team list. And when somebody has to type the teams in here, you could compare them against that valid team list. And if they enter a team that's not on the valid team list, you could make the web page say, you know, raise a flag, hey, this team doesn't exist, and help the users catch bugs like that. So it's funny, there's two sections of code in this app. One is like this. We're going to need this page every year. So any enhancements we make to this is going to benefit us for years to come. There's other portions of the scouting app that's game specific, and those will have to change year to year. But enhancements to this would be a really great benefit. If you could submit the patch back to GitHub, we can incorporate it, and everybody can benefit from code like that. So that would be great. It's an area where there's lots of areas in this app that could use help. We've got it working for our needs, but you know, things like this and other analysis are always useful and would be great to have. So lots of opportunity to help with this app from developers. Okay, and then the last link is just alliance selection. So at the end of quals, you've got all your scouting data, you're ready to go, you've been picked into an alliance. Let's scout the elims, and that's what happens here. This is where users, the head scouter comes in, and as soon as the alliances are created, he comes here and selects the alliances. So you pick the event you're at. I've got some events in here pre-configured. So we'll go to week 0 from last year. So who is the Alliance 1 captain? We'll say 1073 is. Who was the Alliance 2 captain? We'll say 150 or 1519. Oh, actually, yeah, that's not the captain. So who did they pick? Who's the captain and who did they pick? So now 151 is the next captain, and they picked 1729. So you can see how this works. And then when it gets down to 8, it adds the second pick as well. So it tries to help follow along with the alliance selection. And once this is done, then those matches are figured out. We know that Alliance 1 will play Alliance 8, Alliance 4 will play Alliance 5. And so the matches are all laid out for your scouters. Okay. So for your scouters, they're going to come to start scouting here. And like we said, you're going to have your event. Once you load your event, looks like we loaded an event here. Okay, well, I'll pick an event that we know, that we went to. Once you load your event, it's going to show up here on this page. And like this top one here, this 2019 QCMO, we have no data on it yet. There's no other entries. For these other matches, these are events that we went to here in New England, and we have some data on it. And in fact, the Granite State, the Granite Regional event, which was week 1 in Salem, New Hampshire, we have event, and we were there for the elims. So we also have Alliance scouting as well. The Alliance is selected. So the way our data works is the app stores data in CSV files, and CSV stands for comma separated value. So it's a very common syntax. It's basically the first line. Well, I can click on the data. The first line is the headers, and then everything is separated by commas. So you can see what the event data looks like. And the value of storing the data in a CSV file is because Excel or spreadsheet or Tableau all know how to read CSV files. So by storing our data in this format, our runner can run over, plug into the scouting app, go to this page, click on CSV file, right click, save as, and now they have all the scouting data downloaded to their laptop. They can now feed that into Tableau, feed it into Excel, feed it into Google Sheets if you have internet. And now they're looking at the data and can do a lot of analysis. A lot of people are very familiar with analyzing the data in spreadsheets. They might have pre-configured formulas and things. So the data is easily shareable to other applications by putting it in this, by storing it in the CSV file. But we also store it in ways to view it as well. So let's take a quick look. Let me just do a quick time check. Okay. Yeah, this is all I wanted to talk about. So your scouters are going to select the event. They're going to pick, all right, how am I viewing the field? Is red to my left and blue to my right, or is red to my right and blue to my left? And also, which robot am I scouting? So I'll be scouting red 2 this event. So you come here, and the match schedule is broken down by robot. So qual 1, my robot is Bob 319, and robot 2. For a match 2, my robot's going to be 151, and for 3, my robot's going to be Mechanical Mayhem. So that's how it lays out, and you can see the qualifiers are laid out here as well. So the alliances were selected, and they're picked here, and now I can scout the quarterfinals, the semifinals. We didn't scout the finals. We figure you want to just enjoy that match. So the user would select the robot, and now this is the app, and it's scaled to fit on a tablet. So it looks a little big on my laptop, but it was designed so that when the browser on our tablets views this fits perfectly on the page without any scrolling. And this is where we get into that UI design. You can see I've grabbed some images from the manual and thrown it in, and basically there's counter buttons. So on the left hand is the auto, and the right hand is the teleop. And we're also tracking missed shots. In case you've got a robot that's missing a lot of shots, that might be interesting to know. Again, it all depends on what your strategy team comes up with. But if you use our default app, this is what we're collecting. You don't even have to collect that. The important things are likely how good are they at hitting the inner port, how good are they at hitting the outer port. We also thought it might be neat to find out if robots shoot from a particular area on the field. So we broke up the field and made it possible for scouters to say, yeah, this robot is shooting from back here. And if I click on that, the page refreshed, and now there's an X where I clicked. So that's the program, storing my click and marking it. So now it knows. It says, okay, he says the robot shot from here, I'll mark an X. And then if the robot shoots from right in front of the port, I click, and then the page refreshed. And because I have to scroll, it jumps like that. But on the tablet, it stays because it all fits. So we thought it might be interesting if a robot's shooting from one spot only, then they could be easy to defend, for example. But if the X's are all over the place, then you know, this robot, it's going to be hard to defend. He can shoot from anywhere. And then down the bottom, I don't know, I hope you can see it. I have the picture of me, the video of me in the way, but there's the rotational control as well. And then there's the submit. Actually, I need to move if I'm gonna, okay, here we go. Yeah, the next button. So then once you're done scouting, the scouter would click next, and now you've stored all those shots into the inner port, the outer port, the lower port, and where they shot from. Now there's end game questions, and this is sort of the subjective from the scouter. How did they do? How did they do at end game? Do they play defense? How were they against defense? Did they generate any fouls? And then basically give us an idea. Did you like the robot? And add any comments if you want. So this is what the app collects. And again, all adaptable. If you can think of other questions you want to add, you can download this, install it, and change these questions and collect the data. Once you save the answers, these answers are written to that CSV file, and then the user is brought back to the qual page back here, and they can move on to the next match and scout the next match. So that's how the scouting app works. And then, so once you have some data, then we can take a look at it. So let's click on the analysis button. And so what this does is try to basically do what spreadsheets are going to do. We don't have all the data for the event, so these results are not final. These were the few matches that we managed to scout. We weren't participating in this event. We just went to scout it, see how the game was going to be played. So you can see, basically we list out all the information that we scouted. We calculate an OPR. It's not the same calculation that Blue Alliance does because now we have per robot data. So we basically say if he got off the auto line, he got 5 points. So 5 points plus he shot 18, Team 95, the Grasshoppers shot 18, we scouted into the outer port. So 18 times 2 plus 5, and that's how we calculate the OPR. Again, if it's not accurate, fix it. If there's a bug in the calculation, you're welcome to fix it, or enhance the calculations. And then, sorry, I'm saying developers can enhance it. But we also made this available to be used as a pick list as well. So as teams are selected, you can pick them off the side here if everybody's getting picked, to help our head scouter and anyone scouting be able to follow along with the selection. And then we also made it possible, so if you're looking for a team, so now we're looking for a robot that can climb, for example. My Zoom window keeps getting in the way. So you might want to click average number of climbs, and that sorts the teams by the teams that climbed. And now we see, oh, maybe we want 61, 61, because their OPR with climbing they're not their OPR. We're not sorting by OPR anymore. We're sorting by their average number of climbs, and they're one of the best remaining robots that were able to climb for climbing. That's the idea behind this page. So, and you can click on individual teams and see how they did. So we can click Bob, and the one match we saw, we didn't collect any scouting data on outer, and during teleop they got 8 in the outer port. So you can see the individual data and where they shot from and things like that. So you can see the individual data. And then finally, so all the data is available for viewing on the web page as well as in the CSV file. And then we also have a prediction. So if we're going to calculate OPR, can we do some predictions? So what happens if we have a team with Mayhem and the I'm drawing a blank, the Knights, right? 1058 PVC Pirates and Bob, and they were going to play against a team with 1073 is not here because we didn't play. So let's just pick 131, 133, and 151. Well, this calculates up the OPR that we gathered, which, like I said, is not accurate. It was just the one day we went. It adds up the OPR and it says the Red Alliance would score 102 and the Blue Alliance would score 90. So it looks like the Red Alliance has a slight advantage based on scouting data that we've collected so far. And it breaks it down. And again, one thing, we didn't see anybody use the rotational control here, but one calculation, this really just adds up the OPR score. And if you pick 3 robots on an alliance that all rotated, then they're going to be, that could be the difference and could be a bug in the calculation here. So we'll want to fix things like that for this year's match. You'll want to say,
Oh, I'm sorry if I'm interrupting. We are near the end, and there were some questions in the chat.
Oh, excellent.
So
yes.
From YouTube.
Yep.
And
that's perfect.
The first question that I want to ask is, some teams use Bluetooth to connect to the tablets to the central server. Have you explored using Bluetooth instead of the wired network?
Yes, exactly. That's a great question. And yes, we did use that. Our previous app, which was written in Java, used Bluetooth to connect to the central server. And that worked well. The biggest challenge, I think, with that was just keeping up with the Java libraries. As some of our tablets got old and new tablets came along, you had to find the matching Java library and the right Bluetooth support. And that's where that app became a challenge, is keeping up with the libraries to match the tablets that we had. So that's where we ended up moving off from that. But yes, we used Bluetooth and that worked really well for us in our previous app.
So if there wouldn't be a convenience of, so let's say you have a team and it is used to switching from Java libraries, would you say that if the Java libraries wouldn't be a problem, it would be more effective, more portable, or would you still?
Yeah, so that's that's sort of the trade-off from our previous solution to this one. You could go either way. I'm not saying one's better than the other. You're right. One restriction with this solution is the wires. It means your scouting team has to sit together, right? You could create multiple Raspberry web servers and split off the team that way, and then you'll have to aggregate the data. But with a Bluetooth solution, you're right, you can send your scouters everywhere, and that might be better because, especially with this year's game, it's going to be hard to see if they hit the inner port versus the outer port. So you might want your scouters strategically. You might want your red scouters sitting in one spot and your blue scouters sitting in another spot. So that would be an advantage to using a solution where Bluetooth was your data transfer protocol. But we decided to go with the wired. Most of our scouters were always sitting together, so we felt that the wired solution would work best. But yeah, there's certainly advantages and disadvantages to this solution. So yeah. Yep, the Bluetooth is an excellent way to get around the data transfer problem.
Yeah. Another one. What were the biggest challenges you encountered while developing this project?
The biggest challenges, I guess the programming gets tricky because the scouting app. So yeah, let's jump into an event. The tricky part is writing, because you're writing scripting code to print HTML and to store data. It gets tricky. If you look along the top, you can see what's going on. So here's the program that's being run, and here are the arguments, the information that's stored so far. And so the challenge is, now you start clicking. So I click on an inner port and I start counting, and you can see the arguments list grows because now I'm storing the scouting data. And so you can see I clicked 2 in auto, and you can see the 2 here in auto. If I come down 1, the 2 becomes 1. So you can see where the data is being stored. So the programming can be the biggest challenge, because you need to make sure that your program is storing and passing. You don't want to lose any information. So every link, if I don't know if you can see it, but down in the lower left in my browser, every button is actually a web link with that
Okay, yeah.
with the same
So
numbers
it
plus another counted. Yep. So it can be tricky to keep track of. Comments I recommend in code can help keep track of that. So the programming can get tricky. I would say that's the trickiest part.
Yeah. And the last question: how long did developing this app take?
It actually it didn't. It took a couple of months. Took a couple of months to get the basics up. So just to get the scouting app, the analysis, the prediction, the head scouter pages sort of came later. The scouting pages here are the trickiest, because you have all these links that you're creating in the page, and each link is taking the arguments that you have, your current state of your data up at the top, and then adding one to, adding +1 for an up arrow and adding -1 for a down arrow. So that can be the trickiest part. And then the other stuff sort of came after. Once we had all this data, for example, the prediction, we're like, oh, we have the data. Let's make it possible to create alliances and predict and calculate their OPR. So that came later. The head scouter obviously was we needed to figure out how to add match data in. So that took some time. But now that it's here and available, really the only maintenance is going to be changing the scouting app pages, which are 2 or 3 pages. And then we'll have to update the prediction and the analysis pages to match the game, the game scoring. But all the other pages, the head scouter pages, the front end pages of selecting events, those will just work with any game from here on out. So
yeah, that's like, to me this is a really great idea. So while I was watching your presentation, I was thinking maybe if there would be a version for FTC, so this for the FRC game, maybe a version for FTC would be developed. Thank you very much for
you're welcome.
being here and presenting this. It was really a pleasure to see, because I looked into parts of your project, let's say the parts you used for a project, let's say the Raspberry Pi and web servers, because I wanted to use those, and I couldn't find a tutorial or something to use them. And maybe with your app, while looking into it, maybe I get a deeper grasp of these concepts. So thank you.
Definitely, yes. Use any part of it. That's great.
Yeah. Thank you very much for being here.
Thank you. Take care.
Yeah. Bye.
Bye.
So, thank you for joining us for the past 3 hours. I know I've learned a lot, and hope you have as well. I'd like now to hand over the stream to our friends from FRC team 1241, who will be hosting the stream for the next shift. So while we're making the transition, let us wait for them to come over. Thank you very much.